Exoplanets, or planets beyond our solar system, exhibit a stunning variety of weather phenomena. While Earth's weather can be intense, it's nothing compared to the extremes found on some of these distant worlds. Today, we'll explore the most dangerous and bizarre exoplanet weather discovered so far, offering a glimpse into the extraordinary climates of these alien planets. Giant gas planets orbiting very close to their stars experience temperatures that make our hottest days seem like a cool breeze. These scorching temperatures, often exceeding thousands of degrees Celsius, result in extreme atmospheric conditions. The proximity to their stars causes these planets to have blistering, unrelenting heat, leading to dynamic and hostile environments. One such planet, WASP 121b, showcases these intense conditions vividly. Tidally locked planets, where one side perpetually faces their star and the other remains in darkness, exhibit eternal day on one side and eternal night on the other. This creates dramatic climate variations between the two sides. The day side can be extremely hot, while the night side remains frigidly cold. The stark contrast drives powerful atmospheric circulation, leading to unique and extreme weather patterns. Proxima Centauri b, a nearby exoplanet, serves as a fascinating example. Supersonic winds, reaching speeds of thousands of kilometers per hour, rage across some exoplanets. These extreme winds are driven by rapid rotation and intense heat differences. Scientists measure these winds using sophisticated instruments, revealing their impact on atmospheric dynamics and planetary surfaces. HD 80606b, with its eccentric orbit and extreme winds, offers a dramatic illustration of these forces at play. Imagine a world where it rains glass. On the exoplanet HD 189733b, this is a reality. Winds whip silicate particles into the atmosphere, which then cool and condense into glass, raining down in shards. This extraordinary weather phenomenon results from the planet's unique atmospheric composition and extreme heat. Visualizations and artist impressions bring this alien landscape to life, showcasing the breathtaking and perilous conditions. Some exoplanets have metal clouds and iron rain. These planets, like WASP 76b, exhibit temperatures high enough to vaporize metals, forming metal clouds. As these clouds cool, they precipitate iron and other metals, raining down in molten droplets. This process profoundly impacts the planet's atmospheric dynamics and surface conditions, making these worlds truly alien in their weather patterns. Exotic clouds composed of carbon and sulfur compounds create otherworldly skies on some exoplanets. These clouds form through complex chemical reactions, significantly influencing the planet's climate and weather. Their presence affects visibility and the accuracy of observations, posing challenges for scientists. Kepler 7b, with its reflective clouds of silicates and metallic compounds, illustrates the diversity of exoplanetary atmospheres. Acid rain, much more corrosive than anything on Earth, falls on some exoplanets. The chemical composition of these planets' atmospheres results in precipitation of sulfuric or hydrochloric acid. This rain can have severe effects on planetary surfaces, eroding and reshaping the landscape. Detection methods include analyzing spectral data to identify the presence of acidic compounds. Kepler 31b is a prime candidate for such corrosive weather. High-gravity planets, significantly more massive than Earth, experience extreme atmospheric pressure. This intense pressure affects weather patterns, creating dense and dynamic atmospheres. Understanding these environments helps scientists gauge the potential for life in high-gravity conditions. OGL 2005 BLG 390LB, a super-Earth, demonstrates the fascinating and complex weather systems driven by high gravity. The future of exoplanet weather research holds immense potential. Upcoming space missions, coupled with advances in detection technology, promise to unveil even more extraordinary weather phenomena. These discoveries will deepen our understanding of planetary climates and their potential for hosting life. As we continue to explore these alien worlds, each finding brings us closer to unraveling the mysteries of the universe and our place within it. Exoplanets are planets that orbit stars outside of our solar system. Unlike the familiar planets around our Sun, exoplanets are located in distant star systems, often light years away from Earth. These planets can vary widely in size, composition, and orbit, offering a diverse array of planetary environments to study. The term exoplanet comes from extrasolar planet, indicating its location beyond our solar system. The first confirmed detection of an exoplanet occurred in 1992, and since then, thousands of exoplanets have been discovered. These discoveries have expanded our understanding of the universe and the variety of planetary systems that exist. Exoplanets can be classified into several types based on their characteristics. These include gas giants like Jupiter, rocky planets similar to Earth, and ice giants resembling Neptune. There are also exotic categories such as hot Jupiters, super-Earths, and mini-Neptunes. Each type presents unique features and conditions that contribute to the diversity of exoplanetary systems. Gas giants are among the most commonly discovered exoplanets due to their large sizes and strong gravitational effects on their host stars. These planets are composed mainly of hydrogen and helium, similar to Jupiter and Saturn in our solar system. Their massive atmospheres and potential for extreme weather make them fascinating subjects of study. Rocky exoplanets, like Earth and Mars, are composed primarily of silicate rocks and metals. These planets are of particular interest to scientists searching for potentially habitable worlds. Understanding their geologic activity, atmospheric composition, and surface conditions can provide insights into the possibilities for life beyond Earth. Super-Earths are a type of exoplanet with masses greater than Earth's, but significantly less than those of ice giants like Uranus and Neptune. These planets can have diverse compositions and environments, ranging from rocky surfaces to thick gaseous atmospheres. Studying super-Earths helps scientists explore a range of planetary conditions that could support life. Ice giants are exoplanets with compositions similar to Neptune and Uranus, featuring thick atmospheres of hydrogen, helium, and icy compounds like water, ammonia, and methane. These planets often have dynamic weather systems driven by internal heat and atmospheric composition. Investigating ice giants enhances our understanding of planetary formation and atmospheric dynamics. Hot Jupiters are a subset of gas giants that orbit very close to their host stars. These planets experience extreme temperatures and intense radiation, leading to unique atmospheric phenomena such as high-speed winds and cloud formations of exotic materials. Hot Jupiters provide a natural laboratory for studying the effects of proximity to a star on planetary weather and climate. Mini-Neptunes are smaller versions of ice giants, with thick gaseous atmospheres and potentially substantial water content. These planets can offer insights into the transition between rocky and gaseous planetary types. Understanding mini-Neptunes aids in comprehending the diversity of exoplanetary atmospheres and their potential for habitability. The discovery of exoplanets has revolutionized our understanding of planetary systems and the potential for life elsewhere in the universe. Each exoplanet detected adds to the growing catalogue of known worlds, offering new opportunities for scientific exploration. The study of exoplanets combines observations from powerful telescopes with advanced modeling techniques to unravel the complexities of these distant worlds. Transit observations involve monitoring the light from a star as an exoplanet passes in front of it, causing a temporary dimming. This method provides crucial information about the planet's size, orbit, and atmospheric properties. Transit observations have been instrumental in identifying thousands of exoplanets and characterizing their atmospheres. Radial velocity measurements detect the gravitational influence of an exoplanet on its host star, causing the star to wobble slightly. This technique reveals the planet's mass and orbital parameters. Combined with transit data, radial velocity measurements help determine the density and composition of exoplanets. Direct imaging of exoplanets involves capturing visual or infrared light from the planet itself, separate from the star's light. This challenging technique is most successful for large, young planets orbiting far from their stars. Direct imaging allows detailed study of exoplanet atmospheres and surface conditions. Atmospheric spectroscopy analyzes the light passing through or reflected by an exoplanet's atmosphere to identify its chemical composition. This technique can detect molecules like water, carbon dioxide, and methane, providing insights into the planet's climate and potential habitability. Spectroscopy is a powerful tool for understanding the atmospheric dynamics of exoplanets. Space missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TS, have been at the forefront of exoplanet discovery. These missions continuously monitor large areas of the sky, detecting exoplanet transits and gathering data on their characteristics. The wealth of information from these missions has significantly advanced our knowledge of exoplanets. Studying exoplanet weather is crucial for understanding the diverse conditions that exist beyond our solar system. By investigating these weather patterns, scientists can gain insights into the atmospheric dynamics, composition, and climate of these distant worlds. This knowledge helps us build a more comprehensive picture of planetary systems across the galaxy. Exoplanet weather studies also provide valuable information about the potential habitability of these planets. By examining atmospheric conditions such as temperature, pressure, and chemical composition, researchers can identify exoplanets that might support liquid water and, consequently, life. This search for habitable environments is a central goal of exoplanet research. Weather patterns on exoplanets can reveal important details about their atmospheres and surface conditions. For instance, the presence of clouds, winds, and precipitation can help scientists understand the energy balance and climate systems of these planets. This information is essential for modeling exoplanetary climates and predicting their behavior over time. Extreme weather phenomena, such as supersonic winds, metal rain, and temperature extremes, highlight the diversity of exoplanetary environments. Studying these phenomena enhances our understanding of the physical processes that drive weather on different types of planets. This knowledge can be applied to improve our models of planetary atmospheres and weather systems. Investigating exoplanet weather can also provide clues about the formation and evolution of planetary systems. Weather patterns and atmospheric composition are influenced by a planet's history, including its formation, migration, and interactions with its host star and other planets. Understanding these factors helps scientists piece together the complex puzzle of planetary system development. Exoplanet weather research can inform our understanding of the potential for life elsewhere in the universe. By identifying planets with stable, temperate climates, scientists can narrow down the search for extraterrestrial life. Additionally, studying extreme weather conditions can help us understand the limits of habitability and the resilience of life in diverse environments. The study of exoplanet weather contributes to our knowledge of atmospheric chemistry and physics. By analyzing the spectra of exoplanet atmospheres, researchers can detect the presence of various molecules and elements. This information helps scientists refine their models of atmospheric processes and better understand the conditions necessary for different weather phenomena. Weather patterns on exoplanets can also shed light on the interactions between planets and their host stars. Stellar radiation and magnetic activity can significantly influence a planet's atmosphere and climate. By studying these interactions, scientists can better understand the role of stars in shaping planetary environments and weather systems. Exoplanet weather research can lead to technological advancements in observational techniques and instruments. The need to detect and analyze distant exoplanet atmospheres drives the development of more sensitive and precise tools. These advancements can have broader applications in astronomy and other scientific fields, benefiting our overall understanding of the universe. Understanding exoplanet weather helps contextualize our own solar system's weather and climate. By comparing Earth's weather patterns with those of other planets, scientists can identify unique and common features. This comparative planetology approach provides a deeper understanding of the fundamental processes that govern planetary atmospheres. The study of exoplanet weather can inspire new theories and models in planetary science. The discovery of unexpected or extreme weather phenomena challenges existing paradigms and prompts the development of new ideas. This process of scientific inquiry and revision drives progress in our understanding of planetary systems. Research on exoplanet weather can also enhance our knowledge of atmospheric escape and retention. Extreme weather conditions can lead to the loss of atmospheric gases into space, influencing a planet's long-term climate and habitability. Studying these processes on exoplanets helps scientists understand the factors that determine atmospheric stability and composition. Investigating the weather on exoplanets can provide insights into their geological activity. For example, weather patterns influenced by volcanic eruptions or tectonic activity can reveal information about a planet's internal dynamics. This knowledge contributes to our understanding of planetary geology and its impact on atmospheric conditions. Exoplanet weather research has the potential to uncover new and exotic meteorological phenomena. The discovery of weather patterns unlike anything seen in our solar system expands our understanding of the possible diversity of planetary environments. These findings enrich our knowledge of the universe and highlight the incredible variety of planetary systems. Studying exoplanet weather fosters international collaboration among scientists, astronomers, and institutions. The complex and interdisciplinary nature of this research requires expertise from various fields, encouraging cooperation and the sharing of knowledge. This collaborative approach enhances the quality and scope of exoplanet weather studies, driving scientific progress forward. Known exoplanet weather phenomena showcase a vast array of extreme and exotic conditions, far beyond anything experienced on Earth. These phenomena provide insights into the complex and dynamic atmospheres of distant worlds. Hot Jupiters are known for their scorching temperatures, often exceeding 2,000 degrees Celsius. These intense temperatures can lead to the formation of exotic clouds and high-speed winds, making them some of the most extreme weather systems in the universe. One of the most fascinating phenomena is the existence of glass rain. On planets like HD 189733b, silicate particles condense into glass and fall from the sky. This occurs under extreme temperatures and wind conditions, creating a hazardous environment of constant glass storms. Iron rain is another striking example of exoplanet weather. On WASP 76b, temperatures are high enough to vaporize iron, which then condenses and falls as molten droplets. This metal rain indicates the presence of extreme atmospheric processes and high temperature fluctuations. Supersonic winds, reaching speeds of thousands of kilometers per hour, are common on many exoplanets. These winds can redistribute heat around the planet, leading to significant differences in temperature and atmospheric pressure between the day and night sides. Tidally locked planets, which always show the same face to their star, experience perpetual daylight on one side and eternal night on the other. This results in dramatic climate variations and can cause powerful winds and unusual weather patterns due to the extreme temperature contrast. Some exoplanets have been found with exotic clouds composed of compounds like sodium, potassium, and even vanadium oxide. These clouds can reflect or absorb light in different ways, affecting the planet's albedo and influencing its overall climate. Acid rain, much more corrosive than anything on Earth, has been detected on exoplanets such as Kepler-31b. This rain can be composed of sulfuric or hydrochloric acid, indicating a highly reactive and volatile atmosphere. Thermal inversions, where the temperature increases with altitude, have been observed in the atmospheres of some exoplanets. This phenomenon can lead to unique weather patterns and has implications for the planet's atmospheric chemistry and heat distribution. High-gravity exoplanets can experience extreme atmospheric pressure, affecting weather systems and climate stability. On these planets, the atmospheric density can lead to unique weather phenomena, influenced by intense gravitational forces. Planets orbiting red dwarf stars often face intense stellar activity, including flares and radiation storms. This stellar weather can strip away atmospheres and dramatically influence the climate and habitability of these planets. The discovery of rogue planets, which do not orbit any star, suggests that they have their own unique weather systems. Without a nearby star, these planets rely on internal heat sources, leading to completely different atmospheric dynamics compared to star-bound exoplanets. The presence of water clouds and potential water rain has been suggested on some exoplanets. While not yet confirmed, this possibility excites scientists as it could point towards more Earth-like weather systems in the universe. Carbon-rich exoplanets might have entirely different weather patterns, with the possibility of carbon monoxide or methane clouds and rain. These planets challenge our understanding of atmospheric chemistry and weather processes. Observations of exoplanet auroras, driven by interactions between a planet's magnetic field and its host star's solar wind, reveal another layer of atmospheric complexity. These auroras can affect atmospheric dynamics and weather patterns on these distant worlds. When comparing exoplanet weather to Earth's weather, the differences are often stark and dramatic. While Earth experiences a variety of weather patterns, they are relatively mild compared to the extreme conditions found on many exoplanets. Earth's weather is driven by the sun's energy, which creates a balance of heat and cool air. This balance leads to predictable patterns like the jet stream, trade winds, and seasonal changes. On many exoplanets, proximity to their stars or unique atmospheric compositions can lead to far more extreme and less predictable weather. Hot Jupiters, for instance, are exposed to intense stellar radiation that heats their atmospheres to thousands of degrees Celsius. This results in extremely high-speed winds and temperatures that are unimaginable on Earth. Such conditions are far beyond anything our planet has ever experienced. On Earth, rain is composed of water droplets, falling from clouds that form in our relatively mild atmosphere. In contrast, some exoplanets experience rain made of molten glass or iron, a direct result of their extraordinarily high temperatures and unique atmospheric chemistry. Supersonic winds on exoplanets can reach speeds of several thousand kilometers per hour. These winds far surpass the strongest hurricanes on Earth, which top out at around 300 kilometers per hour. Such extreme winds create entirely different weather dynamics and surface conditions. Tidally locked exoplanets face one side permanently towards their star, resulting in eternal day on one side and perpetual night on the other. This leads to extreme temperature contrasts, unlike the relatively even heating and cooling experienced on Earth's day-night cycle. Earth's clouds are primarily made of water vapor, which reflects sunlight and helps regulate temperature. Exoplanet clouds can be made of exotic materials like silicates or metal oxides, influencing their climate and weather in ways that are completely alien to our understanding. Acid rain on Earth, primarily due to industrial pollution, is harmful but limited in scope. On some exoplanets, acid rain can be composed of highly corrosive substances like sulfuric or hydrochloric acid, falling consistently due to the planet's atmospheric composition. Thermal inversions on Earth, while not common, occur when warmer air traps cooler air near the surface, leading to smog and pollution buildup. On exoplanets, thermal inversions might be more frequent or intense, significantly affecting their atmospheric dynamics and weather patterns. High-gravity planets experience atmospheric pressure far beyond anything found on Earth. This can lead to incredibly dense atmospheres and weather phenomena driven by intense gravitational forces, creating environments that are difficult to imagine based on our experience. Stellar flares and radiation storms from red dwarf stars can strip away a planet's atmosphere or cause extreme weather conditions. Earth's magnetic field protects us from solar flares, but many exoplanets lack such protection, leading to far more volatile and destructive weather. Rogue planets, which do not orbit a star, rely on internal heat sources for their weather systems. Earth's weather is entirely dependent on the sun, but rogue planets have atmospheres shaped by geothermal heat, resulting in weather patterns that are entirely different from anything seen on Earth. Water clouds and rain are fundamental to Earth's weather system, influencing climate and ecosystems. On some exoplanets, similar clouds might exist, but the potential for other types of precipitation, like methane or ammonia rain, suggests a wide variety of weather patterns unlike anything on our planet. Carbon-rich exoplanets might feature weather dominated by compounds like methane or carbon monoxide, leading to entirely different climate dynamics. Earth's carbon cycle is critical to life, but on these planets, carbon compounds could create exotic weather patterns and environments. Auroras on Earth are spectacular displays caused by interactions between the solar wind and our magnetic field. On exoplanets, auroras can be much more intense and widespread, possibly affecting the planet's atmosphere and weather in significant ways, driven by their unique magnetic environments. The transit method is one of the most successful techniques for detecting exoplanets. It involves monitoring the brightness of a star over time to look for periodic dips in light. These dips occur when a planet passes in front of the star, temporarily blocking some of its light. When an exoplanet transits its star, it creates a small but measurable decrease in the star's brightness. By carefully observing these light curves, astronomers can determine the size and orbital period of the planet. This method is particularly effective for finding large planets close to their stars. The amount of light blocked by the planet depends on its size relative to the star. Larger planets block more light, creating deeper transits. By analyzing the depth and duration of the transit, scientists can estimate the planet's radius and its distance from the star. One of the major advantages of the transit method is that it allows for the detection of multiple planets in the same system. If a star has several planets, each one can create its own distinct transit signal. This has led to the discovery of complex planetary systems with multiple transiting planets. The Kepler Space Telescope has been instrumental in discovering thousands of exoplanets using the transit method. Kepler monitored over 150,000 stars for more than 4 years, providing a wealth of data that has revolutionized our understanding of planetary systems. One challenge of the transit method is that it requires precise and continuous observations. A planet must pass directly between its star and the observer, which means only a small fraction of planetary systems are aligned favorably for transits to be observed. This alignment is known as the line of sight. The transit method can also provide information about a planet's atmosphere. When a planet transits its star, some of the starlight passes through the planet's atmosphere. By analyzing the resulting spectrum, astronomers can identify the chemical composition of the atmosphere and look for signs of gases like hydrogen, water vapor, and methane. Transit timing variations, or TTVs, occur when the gravitational influence of another planet causes deviations in the timing of a planet's transits. These variations can provide clues about additional planets in the system, even if they do not transit the star themselves. The transit method is highly effective for finding planets around relatively small and dim stars, such as red dwarfs. The smaller the star, the larger the relative size of the planet, making transits easier to detect. This has led to the discovery of many Earth-sized planets in the habitable zones of red dwarfs. The precision of the transit method has been enhanced by space-based telescopes like Kepler and TESS, which avoid the distortions caused by Earth's atmosphere. Ground-based observatories also contribute to transit detections, especially for confirming and following up on space-based discoveries. Transit observations have revealed a wide variety of exoplanets, from small rocky worlds to large gas giants. They have also uncovered unusual planetary types, such as ultra-short-period planets that orbit their stars in just a few hours, and planets with highly eccentric orbits. One of the exciting aspects of the transit method is its potential to find planets in the habitable zone, where conditions might be right for liquid water to exist. Several Earth-sized planets have been discovered in the habitable zones of their stars, raising the possibility of finding potentially habitable environments. The transit method has also been used to study the composition and structure of exoplanetary systems. By analyzing the frequency and distribution of transiting planets, scientists can learn about the processes that lead to planet formation and the diversity of planetary systems. In some cases, transits can reveal the presence of planetary rings or moons. These additional bodies can cause variations in the transit light curve, providing indirect evidence of their existence. Detecting exomoons and rings adds another layer of complexity and richness to our understanding of exoplanetary systems. Future missions like the James Webb Space Telescope and the European Space Agency's Plato mission will continue to use the transit method to search for exoplanets and study their atmospheres in greater detail. These missions promise to expand our knowledge of distant worlds and bring us closer to finding potentially habitable planets. The radial velocity method, also known as the Doppler method, is another powerful technique for detecting exoplanets. It measures the changes in a star's velocity due to the gravitational pull of an orbiting planet. As the planet orbits, it causes the star to move in a small orbit around their common center of mass. This movement induces a Doppler shift in the star's light, causing its spectral lines to shift towards the blue when the star moves towards us and towards the red when it moves away. By observing these shifts, astronomers can determine the star's radial velocity, which indicates the presence of an orbiting planet. One of the strengths of the radial velocity method is its ability to measure a planet's minimum mass. The amplitude of the star's velocity changes depends on the planet's mass and its distance from the star. By analyzing these changes, scientists can estimate the planet's mass, although the exact value also depends on the inclination of the planet's orbit. The radial velocity method was instrumental in the discovery of the first exoplanet around a Sun-like star, 51 Pegasi b, in 1995. This groundbreaking discovery confirmed that other stars host planets and opened up a new field of astronomical research. This method is particularly effective for detecting large planets close to their stars, known as hot Jupiters. These planets exert a strong gravitational pull on their stars, creating significant velocity changes that are easier to detect. However, improvements in technology have also allowed the detection of smaller planets further from their stars. One of the challenges of the radial velocity method is the need for precise and stable instruments. Detecting the tiny velocity changes caused by distant planets requires highly sensitive spectrographs and long-term observation campaigns. Modern instruments can detect velocity shifts as small as a few meters per second. The radial velocity method provides important information about the planet's orbit. By studying the periodicity and shape of the velocity curve, astronomers can determine the orbital period and eccentricity of the planet's orbit. This helps in understanding the planet's dynamics and its interactions with other planets in the system. This method also complements the transit method. When a planet is detected using both methods, scientists can determine both its mass and radius, leading to an accurate measurement of its density. This information is crucial for understanding the planet's composition and structure. The radial velocity method can also reveal the presence of multiple planets in a system. Variations in the star's velocity curve can indicate the gravitational influence of additional planets, even if they are not detectable by other means. This has led to the discovery of many multi-planet systems. One limitation of the radial velocity method is its difficulty in detecting planets around very young or very active stars. Stellar activity, such as spots or flares, can create noise in the velocity measurements, making it harder to identify the signals caused by orbiting planets. Advanced data analysis techniques are used to separate these effects. This method has been particularly successful in finding planets around nearby stars. Close stars produce stronger and clearer signals, making it easier to detect their planets. As a result, many of the known exoplanets have been discovered around stars within a few hundred light-years of Earth. The radial velocity method also provides insights into planetary system formation and evolution. By analyzing the distribution of planet masses and orbital characteristics, scientists can test models of how planets form and migrate within their systems. This helps in understanding the diversity of planetary systems in the galaxy. Future advancements in the radial velocity method aim to improve sensitivity and precision. New spectrographs and observation techniques are being developed to detect even smaller velocity changes, potentially revealing Earth-sized planets in the habitable zones of their stars. The European Space Agency's Gaia mission is expected to contribute significantly to radial velocity studies. Gaia will provide precise measurements of stellar positions and motions, which can be combined with radial velocity data to improve the accuracy of planet detections and orbital parameters. The synergy between the radial velocity method and other detection techniques, such as direct imaging and astrometry, will continue to enhance our understanding of exoplanets. Combining different methods allows for more comprehensive studies of planetary systems, providing a fuller picture of their characteristics and behaviors. Direct imaging is a method that involves capturing actual images of exoplanets by blocking out the light from their host stars. This technique allows scientists to study the light directly reflected or emitted by the planets, providing unique insights into their characteristics. The primary challenge of direct imaging is the overwhelming brightness of the stars compared to their planets. Stars can be billions of times brighter than the planets orbiting them, making it extremely difficult to separate the planet's light from the star's glare. To overcome this challenge, astronomers use instruments called coronagraphs and starshades. Coronagraphs are devices within telescopes that block the star's light, allowing the much fainter light from the planet to be detected. Starshades are large, flower-shaped structures positioned in space to cast a shadow over the star, revealing the planets nearby. Direct imaging is particularly effective for finding young, massive planets that are far from their stars. These planets are still hot from their formation and emit infrared light, making them easier to detect with infrared telescopes. One of the significant advantages of direct imaging is the ability to study a planet's atmosphere and surface features. By analyzing the spectrum of the light reflected or emitted by the planet, scientists can determine its atmospheric composition, weather patterns, and even potential signs of habitability. This method has led to the discovery of several exoplanets, including those in the Beta Pictoris and HR 8799 systems. These discoveries have provided valuable data about the formation and evolution of planetary systems. Direct imaging also allows for the study of planetary systems as a whole. Observing multiple planets in the same system provides insights into their interactions and the overall architecture of the system. This holistic view is essential for understanding the dynamics of planetary orbits and their evolution over time. One limitation of direct imaging is its current inability to detect Earth-sized planets in the habitable zones of their stars. The technology required to image such small, distant planets is still in development. Future advancements in telescope design and imaging techniques are expected to overcome this limitation. The James Webb Space Telescope, scheduled to launch soon, will significantly enhance direct imaging capabilities. Its advanced instruments and infrared sensitivity will allow it to capture images of smaller and cooler planets, potentially identifying Earth-like worlds. Direct imaging can also reveal the presence of circumstellar disks, rings, and potential moons around exoplanets. These additional features provide further context for understanding the formation and structure of planetary systems. Studying these features helps scientists learn about the processes that shape planetary environments. One of the most exciting aspects of direct imaging is the potential to detect biosignatures. By analyzing the light from exoplanets, scientists can look for signs of life, such as specific gases that indicate biological activity. This method could eventually help identify planets with conditions suitable for life. Direct imaging complements other exoplanet detection methods, such as the transit and radial velocity techniques. Combining data from multiple methods allows for a more comprehensive understanding of an exoplanet's properties and its environment. The future of direct imaging looks promising, with several new missions and telescopes planned. Projects like the Extremely Large Telescope and the Habitable Exoplanet Observatory aim to push the boundaries of what we can observe, bringing us closer to finding potentially habitable exoplanets. Direct imaging also contributes to the study of brown dwarfs, objects that are intermediate between planets and stars. Observing brown dwarfs helps scientists understand the continuum between the largest planets and the smallest stars, shedding light on the formation and characteristics of both. Ultimately, direct imaging provides a window into the diverse and complex worlds beyond our solar system. Each new image and discovery brings us closer to answering fundamental questions about the nature of planets and the potential for life in the universe. As technology advances, the ability to directly observe these distant worlds will continue to revolutionize our understanding of the cosmos. Atmospheric spectroscopy is a powerful tool for studying the composition of exoplanet atmospheres. By analyzing the light that passes through or is reflected by an exoplanet's atmosphere, scientists can identify the chemical compounds present. When a planet transits its star, some of the starlight passes through the planet's atmosphere. This light is absorbed and re-emitted by the atmospheric gases, creating a spectrum that can be analyzed to determine the composition of the atmosphere. Spectroscopy can detect a wide range of molecules, such as water vapor, carbon dioxide, methane, and oxygen. Each molecule absorbs light at specific wavelengths, creating unique spectral signatures that can be identified. The presence of these molecules can provide important clues about the planet's climate, weather patterns, and potential habitability. For example, water vapor is a key indicator of a planet's potential to support life as we know it. Spectroscopy also allows scientists to study the temperature and pressure of an exoplanet's atmosphere. By analyzing the broadening and shifting of spectral lines, researchers can infer these physical properties and better understand the atmospheric conditions. One of the significant achievements of atmospheric spectroscopy is the detection of water vapor on several exoplanets. This discovery is crucial in the search for habitable worlds, as water is essential for life. In addition to water, spectroscopy has identified other important molecules, such as methane and carbon dioxide, which can provide insights into the planet's geological and biological processes. These findings help build a more complete picture of the planet's environment. Spectroscopy can also reveal the presence of clouds and hazes in an exoplanet's atmosphere. These particles can scatter light and obscure certain spectral features, providing information about the planet's weather and atmospheric dynamics. One challenge of atmospheric spectroscopy is the need for extremely precise measurements. The signals from exoplanet atmospheres are often faint and can be easily overwhelmed by noise from the star or other sources. Advanced telescopes and instruments are required to achieve the necessary sensitivity. Space telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are well suited for atmospheric spectroscopy. Their position above Earth's atmosphere allows them to observe exoplanets without interference from our planet's own atmospheric effects. Ground-based observatories also contribute to atmospheric spectroscopy, using techniques like high-resolution spectroscopy and adaptive optics to enhance their capabilities. These observations complement space-based data and provide additional insights into exoplanet atmospheres. Spectroscopy is not limited to transiting exoplanets. It can also be used to study directly imaged exoplanets, where the planet's light is observed directly rather than through a transit. This approach allows for the analysis of a broader range of exoplanets and their atmospheres. One exciting application of atmospheric spectroscopy is the search for biosignatures, or signs of life. Certain molecules, like oxygen and methane, can be indicative of biological processes. Detecting these gases in an exoplanet's atmosphere could suggest the presence of life. As technology advances, atmospheric spectroscopy will continue to play a crucial role in exoplanet research. New instruments and techniques will improve our ability to detect and analyze the faint signals from distant worlds, revealing more about their atmospheres and potential for habitability. The future of atmospheric spectroscopy is promising, with upcoming missions and telescopes poised to make significant discoveries. These advancements will enhance our understanding of exoplanets and bring us closer to answering the fundamental question of whether we are alone in the universe. Space telescopes and missions have revolutionized our understanding of exoplanets and their atmospheres. These advanced observatories allow us to study distant worlds with unprecedented precision and detail. The Hubble Space Telescope has been a workhorse in exoplanet research. Its powerful instruments have provided critical data on the atmospheres of numerous exoplanets, detecting water vapor, methane, and other important molecules. The Kepler Space Telescope, launched in 2009, was specifically designed to find exoplanets. By monitoring over 150,000 stars for transits, Kepler discovered thousands of exoplanets, vastly expanding our knowledge of planetary systems. The Transiting Exoplanet Survey Satellite, or TESS, is Kepler's successor. Launched in 2018, TESS continues the hunt for exoplanets by surveying the entire sky, focusing on the nearest and brightest stars. This mission aims to find Earth-sized planets in habitable zones. The James Webb Space Telescope, set to launch soon, promises to revolutionize exoplanet research. Its advanced infrared capabilities will allow it to study the atmospheres of smaller, cooler exoplanets, potentially identifying Earth-like worlds. The European Space Agency's CHEOPS mission focuses on characterizing known exoplanets. By precisely measuring their sizes and densities, CHEOPS helps refine our understanding of these distant worlds and their potential habitability. The Gaia mission, also by the European Space Agency, measures the positions and motions of stars with unprecedented accuracy. Gaia's data helps identify the gravitational influences of exoplanets, complementing other detection methods like radial velocity. The Plato mission, planned by ESA, aims to find and study Earth-like exoplanets around Sun-like stars. Plato will combine transit observations with precise stellar measurements to uncover new exoplanets and provide detailed information about their systems. NASA's upcoming Nancy Grace Roman Space Telescope will also contribute to exoplanet research. Its wide-field survey capabilities will allow it to discover new exoplanets and study the diversity of planetary systems in the Milky Way. The Ariel mission, planned by ESA, will focus on the atmospheres of exoplanets. By observing a diverse range of exoplanets, Ariel aims to understand their atmospheric composition, temperature, and chemistry, shedding light on their formation and evolution. The WF-1 mission, now known as the Nancy Grace Roman Space Telescope, will use microlensing to detect exoplanets. This technique is particularly effective for finding planets that are further from their stars, providing a broader picture of planetary system architectures. Future missions like LUVOIR and HabEx are in the conceptual stages. These ambitious projects aim to directly image Earth-like exoplanets and study their atmospheres in detail, searching for signs of habitability and biosignatures. The Exoplanet Survey Satellite, or EXOSAT, is another planned mission focused on detecting and characterizing exoplanets. By studying transits and radial velocity signals, EXOSAT will provide valuable data on the masses and compositions of distant planets. Space-based observatories have distinct advantages over ground-based telescopes. They avoid atmospheric interference, allowing for clearer and more precise observations. This is crucial for detecting the faint signals from exoplanets and their atmospheres. The collaboration between space missions and ground-based observatories enhances our ability to study exoplanets. Ground-based telescopes can follow up on space-based discoveries, providing additional data and confirming the existence of newly detected exoplanets. This synergy between different types of observatories is essential for advancing our understanding of the universe and the diversity of planetary systems within it. Hot Jupiters are a class of exoplanets that are similar in size to Jupiter, but orbit very close to their host stars. These planets experience extreme conditions due to their proximity to the star. The temperatures on hot Jupiters can reach thousands of degrees Celsius, making them some of the hottest planets ever discovered. This intense heat affects their atmospheres, leading to unique weather phenomena. Due to the extreme heat, the atmospheres of hot Jupiters are often composed of vaporized metals and other exotic compounds. These atmospheres can include elements like sodium, potassium, and even titanium oxide. The close orbit of hot Jupiters results in extremely short orbital periods. Many of these planets complete an orbit around their star in just a few days, which contrasts sharply with the longer orbital periods of planets in our solar system.
Hot Jupiters are usually tidally lies, meaning the planet always faces while the other side remains in perpetual darkness. This creates a significant temperature difference between the day side and the night side.
The extreme temperature gradient between the day and night sides drives powerful atmospheric winds. These winds can reach speeds of several thousand kilometers per hour, redistributing heat around the planet. The intense radiation from the host star can lead to atmospheric escape, where lighter elements like hydrogen and helium are stripped away from the planet's atmosphere. This process can significantly alter the planet's atmospheric composition over time. Many hot Jupiters have large, puffy atmospheres. The intense heat causes the outer layers of the atmosphere to expand, making these planets appear larger than they would at cooler temperatures. The high temperatures can also cause the formation of unusual clouds. On some hot Jupiters, clouds might be composed of silicates or metal oxides, resulting in weather patterns that are vastly different from anything seen on Earth. Hot Jupiters often exhibit strong emission spectra due to their high temperatures. These spectra can be used to study the atmospheric composition and dynamics, providing valuable insights into the physical processes occurring on these planets. Despite their harsh conditions, hot Jupiters can have stable atmospheres. The strong winds and heat redistribution can create a dynamic yet balanced atmospheric system, allowing for detailed study over extended periods. The discovery of hot Jupiters challenged previous models of planetary formation. Their existence close to their host stars suggests that they likely formed further out and migrated inward, providing crucial data for theories on planetary migration. Observations of hot Jupiters have revealed that some of them have highly eccentric orbits. This means their distance from the star varies significantly during an orbit, leading to extreme variations in temperature and atmospheric conditions. Studying hot Jupiters helps scientists understand the diversity of planetary systems. These planets provide a natural laboratory for studying the effects of intense stellar radiation and extreme atmospheric dynamics. Future missions and advanced telescopes aim to study hot Jupiters in even greater detail. By observing a wider range of these planets, scientists hope to uncover more about their formation, migration, and the unique physical processes that define them. Temperature extremes on exoplanets can vary widely, often exceeding those found on Earth. These extreme conditions are influenced by the planet's distance from its star, its atmospheric composition, and its orbital dynamics. Hot Jupiters, for example, experience some of the highest temperatures due to their close proximity to their host stars. Temperatures on the day side of these planets can reach over 2,500 degrees Celsius, hot enough to vaporize metals. The temperature difference between the day and night sides of tidally locked planets can be extreme. While the day side faces constant intense radiation, the night side remains in perpetual darkness, leading to temperatures that can drop by thousands of degrees. On some exoplanets, the high temperatures can lead to the formation of molten lava oceans on the surface. These lava worlds are a testament to the intense heat that can be generated by stellar radiation. Ice giants and gas giants that are located far from their stars can experience the opposite extreme. Their temperatures can plummet to hundreds of degrees below freezing, creating thick layers of ice and potentially exotic forms of frozen gases. The presence of a thick atmosphere can significantly influence temperature extremes. For example, an atmosphere rich in greenhouse gases can trap heat, leading to higher surface temperatures, even if the planet is further from its star. Some exoplanets experience seasonal temperature variations due to their elliptical orbits. As these planets move closer to and further from their stars, the temperature can fluctuate dramatically, creating cycles of intense heat and extreme cold. Volcanic activity can also contribute to temperature extremes. On planets with active volcanism, eruptions can release vast amounts of heat and gases into the atmosphere, temporarily raising the surface temperature. The discovery of ultra-hot Jupiters has pushed the boundaries of known temperature extremes. These planets, such as Kelt 9b, can reach temperatures over 4,000 degrees Celsius, hotter than some stars. Atmospheric escape due to extreme temperatures can strip a planet of its lighter elements, altering its composition. This process can lead to significant changes in the planet's climate and weather patterns over time. Extreme temperatures can also affect the potential for habitability. While Earth-like temperatures are necessary for life as we know it, some organisms might adapt to more extreme conditions, potentially expanding the range of habitable environments. High temperatures can lead to unique chemical reactions in an exoplanet's atmosphere. For instance, at very high temperatures, molecules that are stable on Earth can break down and form new compounds, affecting the planet's overall chemistry. Temperature extremes can influence the planet's albedo or reflectivity. Highly reflective surfaces like ice or clouds can reflect a significant portion of the star's light, affecting the planet's temperature balance. The study of temperature extremes on exoplanets helps scientists understand the physical processes that govern planetary climates. By comparing these conditions with those on Earth, researchers can gain insights into the factors that drive atmospheric dynamics. As technology advances, astronomers will be able to measure temperatures on more distant and diverse exoplanets. This will provide a broader understanding of the range of environmental conditions that exist in the universe, shedding light on the potential for life in extreme environments. The atmospheric composition of exoplanets varies widely, influenced by their size, temperature, and formation history. Understanding these compositions helps scientists learn more about the planet's climates and potential for habitability. Hot Jupiters often have atmospheres rich in hydrogen and helium, similar to Jupiter and Saturn. However, the extreme heat can cause more exotic compounds to form, including vaporized metals like sodium and potassium. Some exoplanets have atmospheres dominated by carbon dioxide, especially those that are closer to their stars, and experience intense heat. This can lead to greenhouse effects, making the planet even hotter. Water vapor is a key component in many exoplanet atmospheres, indicating the potential for liquid water under the right conditions. Detecting water vapor is crucial in the search for habitable planets. Methane is another common molecule found in exoplanet atmospheres, especially on cooler planets. Methane can indicate biological processes or chemical reactions in the planet's atmosphere. Oxygen and ozone, if present, can be strong indicators of biological activity. These molecules are produced by photosynthetic organisms on Earth, so their detection on exoplanets is exciting for astrobiologists. On some exoplanets, clouds and hazes composed of complex hydrocarbons, like those found on Titan, Saturn's moon, can form. These aerosols can obscure the lower atmosphere and complicate spectral analysis. Silicate clouds can form on extremely hot exoplanets, where temperatures are high enough to vaporize rocks. These clouds can create reflective atmospheres, affecting the planet's albedo and climate. Iron and titanium oxide are found in the atmospheres of some ultra-hot Jupiters. These compounds can condense into clouds, contributing to the extreme weather patterns seen on these planets. Carbon monoxide is often present in the atmospheres of gas giants and hot Jupiters. It can provide insights into the planet's atmospheric circulation and the chemistry occurring in its upper layers. Sulfur compounds, like sulfur dioxide, can be indicators of volcanic activity or chemical reactions driven by the planet's star. These molecules can also affect the planet's climate and atmospheric dynamics. On colder exoplanets, nitrogen can be a major component of the atmosphere, similar to Earth. Nitrogen-dominated atmospheres can support complex weather systems and potential biospheres. Ammonia, found in the atmospheres of gas giants like Jupiter, can also be present in exoplanet atmospheres. It plays a role in cloud formation and can indicate the presence of complex atmospheric chemistry. Phosphine has recently been proposed as a potential biosignature. Its detection in an exoplanet atmosphere could suggest biological processes, as it is typically produced by microbial life on Earth. Understanding the atmospheric composition of exoplanets helps scientists build models of their weather systems and potential climates. Each discovery adds to our knowledge of how diverse planetary environments can be. The proximity of an exoplanet to its host star has profound effects on its atmosphere and weather patterns. Planets that orbit very close to their stars experience intense radiation, leading to extreme temperatures and dynamic atmospheric conditions. For hot Jupiters, this proximity results in temperatures that can exceed 2,000 degrees Celsius. Such high temperatures cause atmospheric expansion and can strip away lighter elements, altering the planet's composition. Tidally locked planets, which always show the same face to their star, have a permanent day side and a permanent night side. This creates extreme temperature differences between the two hemispheres, driving powerful winds that redistribute heat. Intense stellar radiation can lead to the photodissociation of molecules in the atmosphere, breaking them down into their constituent atoms. This process can change the atmospheric chemistry and impact the planet's climate. The high levels of radiation also lead to atmospheric escape, where particles gain enough energy to leave the planet's gravitational pull. Over time, this can significantly alter the planet's atmosphere, especially for smaller, less massive planets. In close orbits, the strong gravitational forces from the star can cause tidal heating. This heating can drive geological activity and influence the planet's internal structure, potentially leading to volcanism or other tectonic processes. Proximity to the host star can also enhance the greenhouse effect. For planets with atmospheres rich in greenhouse gases, the increased stellar energy can lead to runaway heating, drastically raising surface temperatures. Stars emit different types of radiation, including ultraviolet and X-rays, which can penetrate deep into a planet's atmosphere. These high-energy photons can ionize atmospheric particles, leading to the formation of complex ions and affecting atmospheric dynamics. Planets in close orbits may also experience frequent stellar flares. These flares can inject large amounts of energy into the planet's atmosphere, causing rapid changes in temperature and potentially stripping away the atmosphere over time. For planets within the habitable zone but close to the inner edge, the increased solar energy can cause extreme weather patterns. These planets may experience intense storms, high winds, and other dynamic atmospheric phenomena. The magnetic field of a planet can interact with the stellar wind from its host star. For planets close to their stars, these interactions can create strong auroras and influence atmospheric circulation and weather patterns. Close proximity can lead to synchronous rotation, where the planet's orbital period matches its rotation period. This results in one side always facing the star, creating a stark contrast between the scorching day side and the freezing night side. On the day side of these planets, temperatures can be high enough to vaporize metals and rocks, leading to exotic atmospheric compositions. These conditions can produce unusual weather phenomena, such as metal clouds and rain. The intense stellar energy can also drive complex chemical reactions in the atmosphere, leading to the formation of exotic compounds and aerosols. These reactions can create layers of haze and clouds, affecting the planet's albedo and climate. Understanding the effects of proximity to host stars is crucial for predicting the atmospheres and climates of exoplanets. Each discovery helps refine models of planetary atmospheres and contributes to our knowledge of how planets evolve under different stellar conditions. WASP 121b is one of the most well-studied hot Jupiters, located about 850 light-years from Earth. It orbits its host star every 1.227 days, making it extremely close and exposed to intense radiation. The extreme proximity to its star causes WASP 121b to have a scorching temperature of about 2,500 degrees Celsius on its day side. This heat is high enough to vaporize metals like iron and magnesium. WASP 121b is tidally locked, meaning one side always faces the star while the other side remains in darkness. This results in a stark contrast between the hot day side and the cooler night side. Observations with the Hubble Space Telescope have detected water vapor in the atmosphere of WASP 121b. This discovery provides crucial insights into the planet's atmospheric composition and weather patterns. The intense heat on the day side of WASP 121b causes the atmosphere to expand and escape into space. This phenomenon, known as atmospheric escape, is significant because it alters the planet's long-term atmospheric composition. One of the most striking features of WASP 121b is the presence of metal clouds. The high temperatures cause metals like vanadium and titanium to vaporize and form clouds in the atmosphere. Studies have also suggested that WASP 121b may have a stratosphere, a layer of the atmosphere where the temperature increases with altitude. This is similar to Earth's stratosphere and is caused by the absorption of stellar radiation by molecules like water vapor. The temperature difference between the day and night sides drives powerful winds that circulate heat around the planet. These winds can reach speeds of up to 5 kilometers per second, creating dynamic weather patterns. WASP 121b is an excellent example of a planet experiencing strong atmospheric escape. Observations have shown that heavy metals, such as iron and magnesium, are being lost from the atmosphere, carried away by the intense stellar radiation. The chemical composition of WASP 121b's atmosphere includes exotic compounds not found on Earth. These compounds, such as titanium oxide, contribute to the unique weather and cloud formations on the planet. The extreme conditions on WASP 121b also affect its potential for hosting life. The high temperatures and intense radiation make it an unlikely candidate for habitability as we understand it. WASP 121b's extreme environment makes it a valuable case study for understanding atmospheric dynamics and chemical processes on hot Jupiters. The data collected from this planet help refine models of atmospheric escape and heat redistribution. The planet's close orbit and rapid rotation provide a natural laboratory for studying tidal interactions and their effects on atmospheric dynamics. These interactions can offer insights into the long-term evolution of close-in exoplanets. Future observations with the James Webb Space Telescope aim to study WASP 121b in even greater detail. These observations will focus on the planet's thermal structure, cloud composition, and atmospheric escape processes. WASP 121b continues to be a key target for exoplanet research. Its extreme conditions and unique atmospheric features provide valuable information that enhances our understanding of the diverse and dynamic nature of exoplanets. Tidal locking occurs when an astronomical body always shows the same face to the object it is orbiting. This happens because the body's rotational period matches its orbital period around its partner. This phenomenon is the result of gravitational forces. Over time, these forces cause the rotation of the smaller body to slow down until it matches its orbit. The most well-known example of tidal locking in our solar system is the Moon. The Moon is tidally locked to Earth, so we always see the same side. On tidally locked exoplanets, one hemisphere is in perpetual daylight while the other is in constant darkness. This creates extreme temperature differences between the two sides. The day side of a tidally locked planet can be extremely hot, absorbing the star's energy continuously. In contrast, the night side can be frigid, receiving no direct starlight. Tidal locking is common for planets orbiting very close to their stars, such as hot Jupiters. The intense gravitational forces from the nearby star accelerate the locking process. The process of tidal locking also affects the planet's shape. The gravitational pull from the star can elongate the planet slightly, causing it to bulge towards the star. The dynamics of a tidally locked planet's atmosphere are complex. The extreme temperature gradient between the day and night sides can drive powerful winds and create unique weather patterns. For tidally locked planets in the habitable zone, the region between the day and night sides, called the terminator, may have more moderate temperatures. This area could potentially support life. Tidal locking influences the geological activity of a planet. The gravitational interaction with the star can create tidal heating, affecting the planet's interior and potentially driving volcanic activity. The length of time it takes for a planet to become tidally locked depends on various factors, including its distance from the star, its mass, and its initial rotation rate. Tidal locking can also impact the magnetic field of a planet. A slower rotation can weaken the magnetic field, making the planet more vulnerable to stellar winds and radiation. In binary star systems, tidal locking can occur between the stars themselves if they are close enough. This results in both stars showing the same face to each other. Understanding tidal locking helps scientists predict the climates and potential habitability of exoplanets. It provides insights into the long-term evolution of planetary systems. Studying tidally locked exoplanets offers a glimpse into how planets can adapt to extreme conditions. It expands our knowledge of planetary dynamics and the diverse environments that exist in the universe. On tidally locked exoplanets, the climate variations between the day and night sides can be extreme. The day side is constantly exposed to the star's intense radiation, while the night side remains in perpetual darkness. The day side heats up significantly, often reaching temperatures high enough to vaporize metals. This creates a hot, glowing atmosphere with strong thermal emissions. In contrast, the night side can be incredibly cold, sometimes plunging to temperatures where gases can condense into liquids or solids. This stark temperature difference creates a dramatic contrast between the two hemispheres. The sharp temperature gradient drives powerful winds. These winds can redistribute heat from the day side to the night side, attempting to balance the extreme conditions. On some tidally locked planets, these winds can reach supersonic speeds. They play a crucial role in the planet's atmospheric dynamics, affecting weather patterns and climate. Cloud formations can vary significantly between the day and night sides. The day side may have clouds composed of exotic materials like silicates, while the night side could have clouds formed from condensed gases. The boundary between the day and night sides, known as the terminator, can have more moderate temperatures. This region may act as a transition zone, with complex weather patterns influenced by both extremes. Precipitation on tidally locked planets can be unusual. On the day side, high temperatures can cause materials to vaporize and form clouds, which may precipitate as exotic rains, such as molten metal. The night side might experience different forms of precipitation, including solid particles like snow or ice, depending on the atmospheric composition and temperature. Thermal inversions can occur on tidally locked planets. These inversions create layers where temperature increases with altitude, affecting the atmospheric circulation and the planet's overall climate. The contrast in temperatures can also influence the chemical composition of the atmosphere. Certain compounds might only form or persist on one side of the planet due to the temperature differences. The extreme conditions can lead to unique photochemical reactions. The intense radiation on the day side can break down molecules, creating different chemical environments compared to the night side. Habitability on tidally locked planets is complex. While the extreme day and night sides are harsh, the terminator region might offer more stable conditions that could potentially support life. The atmospheric pressure can vary between the two sides. The hot day side may have lower pressure due to expanded gases, while the night side could have higher pressure where gases condense. Understanding the climate variations on tidally locked exoplanets helps scientists predict their weather patterns and potential for habitability. These insights contribute to our broader knowledge of planetary climates and the diversity of environments beyond our solar system. Atmospheric circulation patterns on exoplanets are driven by various factors, including temperature differences, rotation, and the planet's composition. These patterns play a crucial role in redistributing heat and maintaining climate stability. On tidally locked exoplanets, the stark temperature contrast between the day and night sides generates strong winds. These winds flow from the hot day side to the cold night side, attempting to equalize temperatures. The Coriolis effect, caused by the planet's rotation, influences wind patterns. On rapidly rotating planets, this effect can create complex, swirling atmospheric currents, leading to features like jet streams and cyclones. The strong day-to-night winds can create a pattern known as superrotation, where the atmosphere moves faster than the planet itself. This phenomenon has been observed on Venus and is expected on some exoplanets. Vertical circulation is also important. Hot air rises on the day side, cools as it moves to the night side, and then descends. This cycle, known as convection, helps transport heat across the planet. Hadley cells, which are large-scale atmospheric circulation patterns, can form on exoplanets. These cells involve air rising near the equator, moving toward the poles, and descending in the mid-latitudes, creating distinct climate zones. The interaction between different circulation patterns can lead to complex weather systems. For example, the meeting of Hadley cells and polar winds can create stormy regions with intense precipitation. Atmospheric circulation can also influence cloud formation and distribution. On the day side, rising warm air can lead to the formation of high-altitude clouds, while the night side may have low-lying clouds formed from cooling air. In some cases, exoplanets might have permanent storm systems due to their circulation patterns. These storms can be massive and long-lasting, driven by the continuous heat and wind flow from the day side. The strength and direction of winds can vary with altitude. Higher altitudes may have faster winds due to lower air density, while lower altitudes experience more friction and slower wind speeds. The composition of the atmosphere affects circulation patterns. Heavier molecules like carbon dioxide can lead to different thermal properties compared to lighter molecules like hydrogen and helium, influencing how heat is distributed. Atmospheric circulation also affects the distribution of gases and aerosols. Certain chemicals might accumulate in specific regions, leading to varying atmospheric compositions across the planet. The presence of a magnetic field can interact with atmospheric circulation. Magnetically driven currents and auroras can influence the movement of charged particles, affecting overall circulation patterns. Atmospheric circulation on exoplanets can also be influenced by the presence of moons or rings. These additional bodies can exert gravitational forces that modify wind patterns and create unique climatic effects. Understanding atmospheric circulation patterns on exoplanets is crucial for predicting their weather and climate. These patterns provide insights into the planet's atmospheric dynamics, potential habitability, and overall environmental conditions. The potential for habitable zones on exoplanets is a key focus in the search for life beyond our solar system. A habitable zone is the region around a star where conditions might be right for liquid water to exist on a planet's surface. The distance of the habitable zone from the star depends on the star's temperature and luminosity. For hotter, brighter stars, the habitable zone is farther out. For cooler, dimmer stars, it's much closer in. Liquid water is crucial because it's a solvent for biochemical reactions. The presence of water increases the chances that a planet could support life as we know it. Not all planets in the habitable zone are necessarily habitable. Factors such as atmospheric composition, pressure, and geological activity also play critical roles in determining a planet's potential to support life. For tidally locked planets, the habitable zone might include regions along the terminator, the line between the permanent day and night sides. Here, temperatures could be moderate enough to allow liquid water to exist. Planets in the habitable zones of red dwarf stars face challenges like frequent stellar flares and intense radiation, which can strip away atmospheres and affect their potential habitability. The concept of a continuously habitable zone considers the stability of a star over time. Long-lived stars provide more stable environments for life to potentially develop and thrive. The thickness and composition of a planet's atmosphere are crucial in maintaining surface temperatures within the habitable range. A thick atmosphere can trap heat and prevent the planet from freezing. Geological activity, such as volcanism, can replenish a planet's atmosphere and provide essential nutrients, enhancing its habitability. Plate tectonics on Earth play a significant role in regulating climate and supporting life. Exoplanets with large moons might have stabilized axial tilts, reducing extreme seasonal variations and creating more stable climates conducive to life. The presence of oceans and large bodies of water can help regulate a planet's climate by distributing heat more evenly across the surface, creating more favorable conditions for life. Some planets might have subsurface oceans beneath icy crusts, similar to Jupiter's moon Europa. These oceans, heated by geothermal activity, could provide environments where life might exist. Detecting biosignatures, such as specific gases like oxygen, methane, or ozone, can indicate biological activity. These gases are produced by life on Earth and could be signs of life on other planets. Advanced telescopes and missions like the James Webb Space Telescope and future space observatories aim to study exoplanets in habitable zones more closely, searching for signs of habitability and potential life. Understanding the potential for habitable zones helps scientists prioritize which exoplanets to study in greater detail. This research brings us closer to finding out if we are alone in the universe and understanding the conditions necessary for life to exist. Proxima Centauri b is one of the most intriguing exoplanets discovered, located just over 4 light-years away from Earth. It orbits Proxima Centauri, the closest star to the Sun, within the star's habitable zone. Proxima Centauri b has a mass slightly larger than Earth, making it a super-Earth. Its size and location have led scientists to consider its potential for supporting life. The planet orbits very close to its star, completing a full orbit in just 11.2 days. This proximity means it receives about the same amount of stellar energy as Earth receives from the Sun. Proxima Centauri is a red dwarf, a type of star that is smaller and cooler than the Sun. Red dwarfs are known for their longevity, providing stable energy over billions of years, but they also emit strong stellar flares. Proxima Centauri b is likely tidally locked due to its close orbit. This means one side of the planet is always in daylight, while the other side is in perpetual darkness, creating extreme temperature differences. The habitable zone of Proxima Centauri is much closer to the star than the Sun's habitable zone due to the star's lower luminosity. Proxima Centauri b falls within this zone, raising the possibility of liquid water on its surface. The star's frequent flares pose a challenge for the planet's habitability. These flares can strip away the atmosphere and expose the surface to harmful radiation, which would be detrimental to any potential life forms. Despite these challenges, the presence of a magnetic field could help Proxima Centauri b retain its atmosphere. A strong magnetic field would protect the planet from stellar wind and radiation, similar to how Earth's magnetic field protects us. Future observations aim to detect and study the atmosphere of Proxima Centauri b. Finding an atmosphere would be a significant step in assessing the planet's habitability and potential for supporting life. If Proxima Centauri b has an atmosphere, it could help moderate the temperature extremes between the day and night sides. Atmospheric circulation could transport heat, creating more stable and habitable conditions. The planet's proximity to Earth makes it an excellent target for future missions. Potential missions could include sending probes or even an interstellar mission to study the planet directly. The discovery of Proxima Centauri b has spurred interest in exploring the Alpha Centauri system, which includes Proxima Centauri and its 2 larger companion stars, Alpha Centauri A and B. Proxima Centauri b's potential for life makes it a focal point in the search for extraterrestrial life. Even if it turns out to be uninhabitable, studying it will provide valuable insights into planetary science and the conditions that affect habitability. Understanding Proxima Centauri b helps scientists refine models of exoplanet atmospheres and climates. It also contributes to our knowledge of how planets around red dwarf stars might differ from those around Sun-like stars. The ongoing study of Proxima Centauri b exemplifies the broader quest to find life beyond Earth. Each discovery adds to our understanding of the universe and brings us closer to answering one of humanity's most profound questions. Are we alone in the cosmos? Extreme winds on exoplanets are caused by various factors, including temperature differences, rotational dynamics, and atmospheric composition. These winds can reach speeds far exceeding those found on Earth. One primary cause of extreme winds is the significant temperature gradient between the day and night sides of tidally locked planets. This stark contrast drives powerful winds as the atmosphere attempts to redistribute heat. The rapid rotation of some exoplanets contributes to strong winds through the Coriolis effect. This effect causes moving air to deflect, creating swirling wind patterns and high-speed jet streams. Stellar radiation plays a crucial role in generating extreme winds. Intense heating on the day side of a planet can lead to rapid atmospheric expansion, driving fierce winds toward the cooler night side. Atmospheric circulation cells, like Hadley cells, can also cause extreme winds. These cells involve large-scale movement of air, with rising warm air near the equator and descending cooler air at higher latitudes, creating strong wind currents. Some exoplanets have unusual atmospheric compositions that contribute to extreme winds. For example, atmospheres rich in hydrogen and helium can be less dense, allowing winds to move more quickly. The presence of clouds and aerosols can enhance wind speeds by affecting the planet's albedo and energy balance. Clouds can reflect or trap heat, creating temperature gradients that drive winds. Magnetic fields can influence wind patterns on exoplanets, Interactions between the planet's magnetic field and the stellar wind can create magnetically driven winds and alter atmospheric dynamics. Tidal forces from a nearby star can induce internal heating and drive atmospheric motion. This tidal heating can create temperature differences that lead to strong winds, especially on close-in exoplanets. The presence of multiple planets in a system can create gravitational interactions that affect atmospheric dynamics. These interactions can induce eccentric orbits and variations in atmospheric pressure, leading to extreme winds. Stellar activity, such as flares and coronal mass ejections, can inject large amounts of energy into an exoplanet's atmosphere, temporarily enhancing wind speeds and altering atmospheric circulation. Vertical wind shear, where wind speed changes with altitude, can create turbulent atmospheric conditions. This shear can lead to the development of intense storms and high-velocity winds. Geological activity, like volcanism, can release large amounts of gas and heat into the atmosphere, driving strong winds and influencing weather patterns. Seasonal changes on some exoplanets can cause shifts in wind patterns. If the planet has an axial tilt, varying solar heating throughout its orbit can lead to periodic changes in wind speed and direction. Understanding the causes of extreme winds helps scientists predict weather patterns and climate on exoplanets. These insights are crucial for assessing the habitability and environmental conditions of these distant worlds. Measurement techniques for studying exoplanet weather involve advanced methods to gather data about their atmospheres and surface conditions. These techniques provide insights into the physical characteristics and dynamic processes occurring on these distant worlds. One primary technique is transit photometry, where astronomers observe the light curve of a star as a planet passes in front of it. By analyzing the dips in brightness, they can infer the planet's size and atmospheric composition. Spectroscopy is another crucial method. When a planet transits its star, some of the starlight passes through its atmosphere. By examining the absorption lines in the spectrum, scientists can identify the atmospheric gases and their concentrations. Direct imaging allows astronomers to capture actual images of exoplanets by blocking out the star's light. This technique helps study the planet's atmosphere and surface features, providing detailed information about its weather patterns. Radial velocity measurements detect the wobbling motion of a star caused by the gravitational pull of an orbiting planet. These measurements provide data on the planet's mass and orbital characteristics, which can influence its atmospheric dynamics. Doppler spectroscopy is used to measure the shifts in the star's light spectrum due to the planet's gravitational effects. This method helps determine the velocity and motion of the star, giving clues about the planet's properties. Polarimetry measures the polarization of light reflected from a planet's atmosphere. This technique can reveal details about cloud composition, particle size, and atmospheric structure, offering insights into weather conditions. Astrometry involves precisely measuring the position of a star over time to detect the slight movements caused by orbiting planets. This technique helps determine the planet's mass and distance from the star, influencing its climate. Infrared observations are essential for studying exoplanet atmospheres. Infrared light can penetrate through clouds and reveal thermal emissions, providing data on temperature distribution and heat dynamics. The James Webb Space Telescope will use its advanced infrared capabilities to study exoplanet atmospheres in greater detail, focusing on their thermal structures and atmospheric compositions. High-resolution spectroscopy allows for the detection of minute variations in the light spectrum, helping to identify specific molecules and isotopes in the planet's atmosphere. This technique is crucial for understanding the chemical processes occurring on exoplanets. Time series photometry involves continuous monitoring of a star's brightness to detect variations caused by transiting planets. This method helps study changes in the planet's atmosphere and weather patterns over time. Gravitational microlensing detects exoplanets by observing the bending of light from a distant star due to the gravitational field of an intervening star-planet system. This technique can provide data on planets that are otherwise difficult to detect. Thermal phase curve observations measure the changes in infrared brightness of a planet as it orbits its star. These observations help determine the temperature distribution and heat transport mechanisms in the planet's atmosphere. Ground-based telescopes equipped with adaptive optics can correct for atmospheric distortions, allowing for clearer images and more precise measurements of exoplanet characteristics. Combining data from multiple techniques enhances our understanding of exoplanet weather. By integrating information from transit photometry, spectroscopy, and direct imaging, scientists can build comprehensive models of exoplanetary climates and atmospheric dynamics. The impact on atmospheric dynamics on exoplanets can be profound, shaping weather patterns and climate. Factors such as temperature gradients, planetary rotation, and atmospheric composition play significant roles in these dynamics. Extreme temperature differences between the day and night sides of tidally locked planets drive powerful winds. These winds can redistribute heat, influencing the overall climate of the planet. Rapid rotation rates can lead to strong Coriolis forces, which cause atmospheric currents to bend and create complex wind patterns. These patterns can include jet streams, cyclones, and anticyclones. The presence of a thick atmosphere can enhance greenhouse effects, trapping heat and increasing surface temperatures. This can lead to more stable and uniform temperatures across the planet. Different atmospheric compositions can result in varied weather phenomena. For example, atmospheres rich in hydrogen and helium can produce faster winds due to their lower molecular weight compared to atmospheres with heavier molecules like carbon dioxide. Magnetic fields interact with atmospheric particles, potentially influencing wind patterns and the distribution of charged particles. This interaction can create auroras and affect atmospheric dynamics. Stellar radiation and flares impact atmospheric stability by injecting large amounts of energy. This can cause rapid heating and expansion of the atmosphere, leading to temporary changes in wind patterns and weather systems. The presence of clouds and aerosols affects the planet's albedo, reflecting some of the stellar radiation back into space. This can cool the surface and influence atmospheric circulation patterns. Vertical wind shear, where wind speed changes with altitude, can create turbulence and affect the development of storms. This shear can influence the vertical mixing of atmospheric layers, impacting weather systems. Seasonal variations due to axial tilt can lead to shifts in atmospheric dynamics. As the planet orbits its star, different regions receive varying amounts of sunlight, creating seasonal weather patterns. Atmospheric circulation cells, such as Hadley cells, can transport heat from the equator to higher latitudes. These cells create distinct climate zones and play a crucial role in maintaining thermal balance. On planets with significant geological activity, volcanic eruptions can release gases and particulates into the atmosphere. This can lead to short-term climate changes and influence atmospheric dynamics. The loss of atmospheric gases through processes like atmospheric escape affects the long-term climate. As lighter molecules escape, the composition of the atmosphere changes, which can alter weather patterns and temperature regulation. Interactions between multiple planets in a system can induce gravitational forces that influence atmospheric dynamics. These interactions can cause variations in orbital parameters, leading to changes in climate and weather systems. Studying the impact on atmospheric dynamics helps scientists understand the complex interplay of factors that govern exoplanet climates. These insights are essential for predicting weather patterns and assessing the habitability of distant worlds. The effects on planetary surfaces due to atmospheric dynamics and extreme weather are profound. Intense heat from stellar radiation can cause surface materials to vaporize, leading to unique atmospheric compositions and surface features. On tidally locked planets, the permanent day side can be scorched, while the night side remains frigid. This temperature dichotomy can create significant geological differences between the two hemispheres. High-speed winds can erode surface features, transporting dust and particles across the planet. This erosion can reshape landscapes over time, forming dunes, valleys, and other geological structures. Supersonic winds, driven by extreme temperature differences, can strip away surface layers, exposing underlying rock and altering the planet's topography. These winds can also deposit materials in new locations, creating diverse surface patterns. Intense heat can lead to the formation of lava lakes and volcanic plains, particularly on geologically active planets. These features are shaped by the ongoing release of heat from the planet's interior. On planets with metal-rich atmospheres, metal condensation and precipitation can occur. This could result in metallic surfaces or the accumulation of metal deposits, drastically altering the planet's appearance and composition. Extreme weather, such as storms and hurricanes, can cause significant surface erosion and sediment displacement. These events can carve out new geological formations and impact the distribution of surface materials.
Temperature fluctuations between day and night cycles can cause stress on the planet's crust. This stress may lead to cracking, faulting, and other tectonic activities, altering the planet's geological landscape.
Volcanic activity can be influenced by atmospheric dynamics. For example, tidal heating due to gravitational interactions can increase volcanic eruptions, shaping the planet's surface with lava flows and ash deposits. The presence of large bodies of water, such as oceans or lakes, can moderate surface temperatures and create weather patterns that influence erosion and sedimentation. Water bodies also play a role in the chemical weathering of rocks. Surface temperatures and atmospheric composition can lead to the formation of exotic ices or crystals, particularly on colder planets. These materials can form unique geological structures and affect surface albedo. Impacts from meteoroids and other celestial bodies can create craters and basins, further altering the planet's surface. The frequency and size of these impacts can be influenced by the planet's atmosphere and its protective capabilities. Chemical interactions between the atmosphere and surface materials can lead to the formation of new minerals and surface coatings. These chemical changes can provide insights into the planet's geological history and atmospheric processes. Radiation from the host star can cause surface degradation and the breakdown of organic materials. This radiation can also affect the color and reflectivity of the planet's surface, influencing its thermal balance. Understanding the effects on planetary surfaces helps scientists interpret observational data and model the geological evolution of exoplanets. These insights are crucial for assessing the potential for habitability and the presence of dynamic geological processes on distant worlds. HD 80606b is a fascinating exoplanet located about 190 light-years from Earth in the constellation Ursa Major. This planet is known for its highly eccentric orbit, which takes it extremely close to its host star and then far away again. The orbit of HD 80606b is so eccentric that it experiences dramatic changes in temperature. When it is closest to its star, the planet heats up rapidly, experiencing intense radiation and temperatures that can soar to over 1,000 degrees Celsius. This rapid heating causes the atmosphere to expand and creates powerful winds that redistribute heat across the planet. As HD 80606b moves away from its star, the temperature drops significantly, leading to rapid cooling of the atmosphere. The extreme temperature variations lead to violent weather patterns. The day side of the planet, when it is closest to the star, experiences intense storms and possibly even supersonic winds. Observations using the Spitzer Space Telescope have provided detailed information about these temperature changes. These observations revealed that the temperature on the planet's day side increases by more than 700 degrees Celsius in just a few hours. The rapid heating and cooling cycles on HD 80606b make it a natural laboratory for studying atmospheric dynamics and weather patterns under extreme conditions. These cycles offer insights into how atmospheres respond to intense stellar radiation. The planet's eccentric orbit also affects its atmospheric chemistry. The intense heat during the close approach can break down molecules, while the cooler periods allow for different chemical reactions to occur. HD 80606b's extreme orbit is likely the result of gravitational interactions with a companion star, HD 80607. These interactions have shaped the planet's orbit, leading to the dramatic climate variations observed. The study of HD 80606b helps scientists understand the effects of eccentric orbits on exoplanet climates. It provides a unique opportunity to observe how atmospheric dynamics evolve over a single orbit. The extreme conditions on HD 80606b make it an unlikely candidate for life as we know it. However, studying such extreme environments expands our knowledge of the diversity of planetary systems and the range of conditions they can exhibit. The data collected from HD 80606b also helps refine models of atmospheric circulation and heat distribution. These models are essential for predicting weather patterns on other exoplanets with similar characteristics. Future observations with more advanced telescopes, like the James Webb Space Telescope, will provide even more detailed information about HD 80606b's atmosphere. These observations will help confirm current theories and potentially reveal new insights. The planet's extreme weather conditions offer a valuable case study for understanding atmospheric physics. The findings from HD 80606b can be applied to other exoplanets, enhancing our understanding of atmospheric processes in different environments. HD 80606b's unique characteristics make it a key target for ongoing research. Each observation adds to our understanding of how extreme orbits impact planetary climates and atmospheric dynamics. The study of HD 80606b highlights the importance of diverse planetary systems in expanding our knowledge of the universe. By examining such extreme cases, scientists can better understand the full range of possibilities for exoplanet climates and environments. The formation of metal clouds on exoplanets is an intriguing phenomenon driven by extreme atmospheric conditions. These clouds are composed of vaporized metals like iron and titanium, which condense into cloud particles. On ultra-hot Jupiters, temperatures can soar above 2000 degrees Celsius. At these temperatures, metals can vaporize, becoming part of the planet's atmosphere. As the atmosphere circulates, these metal vapors can be transported to cooler regions. When the temperature drops, the metal vapors condense into tiny solid or liquid particles, forming clouds. The process of condensation depends on the atmospheric pressure and temperature. Higher altitudes with lower pressures are more conducive to the formation of these metal clouds. Spectroscopic observations have detected signatures of these metals in the atmospheres of several exoplanets. For example, iron and titanium oxide have been observed in the atmospheres of some ultra-hot Jupiters. The presence of metal clouds can significantly affect a planet's albedo or reflectivity. These clouds can reflect a large portion of the incoming stellar radiation, impacting the planet's energy balance and climate. Metal clouds can also influence the thermal structure of the atmosphere. By absorbing and re-radiating heat, they can create temperature inversions where the temperature increases with altitude. And these clouds can contribute to the planet's weather patterns. For instance, the condensation and evaporation of metal particles can drive dynamic atmospheric processes, including strong winds and storms. The distribution of metal clouds can vary depending on the planet's atmospheric circulation. On tidally locked planets, these clouds might form on the cooler night side and be transported to the hotter day side. The composition of metal clouds provides insights into the planet's atmospheric chemistry. The specific metals present can reveal information about the planet's formation history and the materials available in its protoplanetary disk. Studying metal clouds helps scientists understand the broader implications of atmospheric processes on exoplanets. These clouds are a key factor in determining the thermal and chemical properties of the planet's atmosphere. The detection of metal clouds is made possible by advanced telescopes and instruments that can analyze the light from these distant worlds. Instruments like those on the Hubble Space Telescope and the upcoming James Webb Space Telescope are crucial for these observations. The presence of metal clouds is not limited to exoplanets. Similar processes might occur on some moons and dwarf planets within our solar system, offering opportunities for comparative studies. Theoretical models help predict where and how these metal clouds form. By comparing these models with observational data, scientists can refine their understanding of atmospheric dynamics on exoplanets. Future research aims to explore the diversity of metal clouds on different types of exoplanets. By studying a wide range of planetary environments, scientists hope to uncover the commonalities and differences in cloud formation processes. Understanding the formation of metal clouds enhances our overall knowledge of planetary atmospheres. It reveals the complexity and variety of weather systems beyond our solar system, contributing to the broader quest to understand the nature of exoplanets. Precipitation of iron and other metals on exoplanets occurs under extremely high temperature conditions. This type of precipitation is a fascinating and exotic weather phenomenon. On ultra-hot Jupiters, temperatures can reach levels high enough to vaporize metals. These vaporized metals, such as iron, can exist in the atmosphere as gaseous particles. When these gaseous metal particles are transported to cooler regions of the atmosphere, they begin to condense. This condensation forms tiny droplets or solid particles, leading to precipitation. Iron rain is one of the most dramatic examples of this process. As the vaporized iron cools, it condenses into liquid droplets, which then fall through the atmosphere, similar to rain on Earth. The precipitation of metals can significantly impact the planet's atmospheric dynamics. The falling metal particles can create dense, reflective layers in the atmosphere, affecting heat distribution. This metal precipitation is often observed on the night side of tidally locked planets. As the hot day side moves vaporized metals to the cooler night side, the metals condense and fall as rain. Titanium oxide is another metal that can precipitate under these extreme conditions. Like iron, it can condense into solid or liquid forms and fall as rain, creating a unique weather system. The presence of metal rain can also influence the surface conditions of these planets. If the metal rain reaches the surface, it can form metallic deposits and alter the planet's topography. The continuous cycle of vaporization and condensation of metals creates dynamic and ever-changing weather patterns. This cycle is driven by the planet's intense heat and atmospheric circulation. Spectroscopic observations have provided evidence of metal precipitation on several exoplanets. These observations detect the spectral signatures of metals in both their vaporized and condensed forms. The study of metal precipitation helps scientists understand the complex interplay between temperature, pressure, and atmospheric composition on exoplanets. It reveals how extreme conditions can produce unique weather phenomena. Theoretical models predict that the size and distribution of metal droplets can vary based on atmospheric conditions. Larger droplets might fall quickly, while smaller particles could be suspended in the atmosphere. Understanding metal precipitation also provides insights into the potential for similar processes on other celestial bodies. Moons, dwarf planets, and even some asteroids might experience metal precipitation under the right conditions. The impact of metal precipitation on a planet's albedo or reflectivity can be significant. These reflective metal layers can affect how much solar radiation the planet absorbs and re-radiates. Future observations with advanced telescopes aim to study metal precipitation in more detail. These studies will enhance our knowledge of exoplanetary weather systems and the diverse conditions that exist beyond our solar system. The impact of metal precipitation on planetary atmospheres is profound, altering their composition and dynamics. As metals vaporize and condense, they influence the thermal structure of the atmosphere. Metal clouds formed by condensed metals can reflect a significant amount of stellar radiation. This reflection affects the planet's energy balance, potentially cooling the atmosphere below the cloud layer. The process of metal precipitation can deplete certain elements from the atmosphere. As metals condense and fall, the atmospheric composition changes, potentially altering chemical reactions and weather patterns. Condensed metal particles can also absorb heat, creating temperature inversions. This means that the temperature increases with altitude in certain atmospheric layers, impacting atmospheric circulation. The redistribution of heat by metal clouds and precipitation can drive powerful winds. These winds help to transport heat from the hot day side to the cooler night side on tidally locked planets. Metal precipitation can also lead to the formation of surface deposits. Over time, these deposits might build up, creating metallic layers or features on the planet's surface. The presence of metal clouds can influence the planet's albedo. Higher albedo means more sunlight is reflected back into space, which can affect the overall climate and temperature of the planet. The continual cycle of vaporization and condensation of metals adds to the dynamic nature of the atmosphere. This cycle contributes to ever-changing weather patterns, driven by the planet's heat and atmospheric movement. Metal precipitation might also impact the potential for habitability. While the extreme conditions of these atmospheres are harsh, understanding them helps scientists assess the environments where life might exist. The detection of metal clouds and precipitation provides valuable data about atmospheric pressure and temperature profiles. These observations help refine models of exoplanetary atmospheres. Studying the impact of metal precipitation helps scientists understand the diversity of exoplanet climates. It reveals how different planets can have vastly different weather systems compared to Earth. The presence of heavy metals in the atmosphere might also affect the planet's magnetic field interactions. These interactions can influence atmospheric loss and the protection of the planet from stellar radiation. Metal precipitation can also contribute to the greenhouse effect. Some metal compounds can trap heat, influencing the thermal dynamics of the atmosphere and potentially leading to higher surface temperatures. Observing metal precipitation in exoplanet atmospheres aids in comparative planetology. By comparing these processes with those on Earth and other planets in our solar system, scientists gain a deeper understanding of planetary atmospheres. Future research will continue to explore the role of metal precipitation in shaping exoplanet atmospheres. Advanced telescopes and instruments will provide more detailed data, enhancing our knowledge of these distant worlds. Observational evidence of metal clouds and precipitation on exoplanets has come from various advanced telescopes and instruments. These observations provide critical insights into the atmospheric dynamics of these distant worlds. The Hubble Space Telescope has played a pivotal role in detecting the signatures of metals like iron and titanium oxide in the atmospheres of hot Jupiters. These detections come from analyzing the absorption lines in the spectra of starlight filtered through the exoplanet's atmosphere. The Spitzer Space Telescope has also contributed to our understanding by measuring the thermal emission from these planets. The variations in infrared light indicate the presence of metal clouds that affect the heat distribution. Ground-based telescopes equipped with high-resolution spectrographs, such as those at the Very Large Telescope, have identified the spectral fingerprints of various metals. These observations help confirm the presence of metal clouds and their composition. The phase curves obtained from observations of hot Jupiters provide additional evidence. These curves show how the brightness of the planet changes as it orbits its star, revealing details about the distribution and movement of metal clouds. Some of the best evidence comes from the day-night temperature differences observed on these exoplanets. The significant drop in temperature from the day side to the night side supports the existence of reflective metal clouds that cool the night side. Detailed analysis of the transit spectra, when the planet passes in front of its star, has shown absorption features corresponding to metals. These features change with altitude, indicating the presence of layered metal clouds. The James Webb Space Telescope, with its advanced capabilities, is expected to provide even more detailed evidence. Its ability to observe in the infrared spectrum will allow for a deeper understanding of the composition and dynamics of metal clouds. Observations during secondary eclipses, when the planet passes behind its star, help isolate the planet's thermal emission. This method provides temperature maps that reveal the effects of metal clouds on the planet's heat distribution. Direct imaging of exoplanets using instruments like those on the Subaru telescope has captured the light directly reflected or emitted by these planets. These images provide direct evidence of cloud formations and atmospheric composition. Polarimetry measurements from telescopes like the Gemini Planet Imager have detected the scattering of light by clouds, including metal clouds. These measurements help determine the particle sizes and compositions within the clouds. Stellar spectroscopy has also shown changes in the light from the host star caused by the exoplanet's atmosphere. These changes indicate the presence of metal-rich clouds affecting the starlight passing through the atmosphere. Comparative studies of multiple exoplanets have revealed consistent patterns in the presence of metal clouds. These patterns suggest common atmospheric processes at play in different planetary systems. Theoretical models, validated by observational data, predict the conditions under which metal clouds form and precipitate. These models help interpret the observational evidence and provide a framework for understanding these exotic weather systems. Ongoing and future missions continue to enhance our observational capabilities. Instruments on the upcoming aerial mission by the European Space Agency aim to conduct a comprehensive survey of exoplanet atmospheres, focusing on chemical compositions and cloud properties. Each piece of observational evidence builds a more complete picture of how metal clouds and precipitation affect exoplanet atmospheres. These insights are crucial for understanding the diverse climates and weather patterns beyond our solar system. WASP-76b is a particularly intriguing exoplanet located approximately 640 light-years away in the constellation Pisces. It is classified as an ultra-hot Jupiter due to its extremely high temperatures. This exoplanet orbits its host star so closely that a single orbit takes only about 1.8 Earth days. This close proximity results in WASP-76b experiencing intense stellar radiation. The day side of WASP-76b reaches scorching temperatures of up to 2,400 degrees Celsius, hot enough to vaporize metals like iron. This extreme heat causes iron in the atmosphere to vaporize, and become part of the gaseous environment. Due to its tidally locked nature, WASP-76b has a permanent day side and night side. The temperature difference between these sides drives ferocious winds that can transport iron vapor across the planet. One of the most fascinating aspects of WASP-76b is the detection of iron rain. Observations suggest that strong winds carry vaporized iron from the hot day side to the cooler night side, where it condenses and falls as iron droplets. The evidence for this metal precipitation comes from high-resolution spectroscopic data. The espresso instrument on the Very Large Telescope detected absorption lines indicating the presence of iron vapor on the evening border of the day side. As the iron vapor is transported to the night side, it cools down and condenses into liquid iron, creating a rain of molten metal. This exotic weather phenomenon is unlike anything seen in our solar system. The continuous cycle of vaporization and condensation of iron significantly impacts the atmospheric dynamics of WASP-76b. This process creates a dynamic and ever-changing atmospheric environment. The presence of iron clouds also affects the planet's albedo and thermal structure. These clouds can reflect some of the incoming stellar radiation, influencing the overall heat distribution in the atmosphere. WASP-76b's extreme conditions and unique weather patterns make it a valuable case study for understanding the atmospheric processes on ultra-hot Jupiters. The findings from this planet help refine models of exoplanetary atmospheres. The study of WASP-76b contributes to our understanding of the chemical interactions in high-temperature environments. The formation and precipitation of metal clouds provide insights into the atmospheric chemistry of hot exoplanets. The extreme weather on WASP-76b also highlights the diversity of planetary climates. By studying such an extreme example, scientists can better grasp the range of atmospheric phenomena that can occur on exoplanets. Future observations with advanced telescopes like the James Webb Space Telescope aim to study WASP-76b in even greater detail. These observations will focus on the planet's atmospheric composition and the dynamics of its metal clouds. The data collected from WASP-76b also help scientists understand how atmospheric circulation works under extreme conditions. These insights can be applied to other hot Jupiters with similar characteristics. WASP-76b continues to be a key target for exoplanet research. Its extreme conditions and the presence of iron rain offer a unique opportunity to study atmospheric processes that are otherwise not observable in our solar system. This research enhances our overall understanding of the complexities of exoplanet atmospheres. Exotic clouds on exoplanets vary widely based on atmospheric composition and temperature. These clouds can form from materials not typically found in clouds on Earth, leading to unique weather phenomena. One type of exotic cloud is composed of silicate particles. On ultra-hot Jupiters, high temperatures can vaporize rock-forming minerals, which then condense into silicate clouds at higher altitudes. Metal clouds are another fascinating type. For instance, on WASP-76b, iron vaporizes on the hot day side and condenses into iron clouds on the cooler night side, creating dramatic weather patterns. Sodium and potassium clouds have been detected in the atmospheres of some exoplanets. These alkali metals, which vaporize at high temperatures, can form clouds that significantly affect the planet's albedo. Titanium and vanadium oxide clouds are also found in some exoplanetary atmospheres. These compounds form at extremely high temperatures and contribute to the complex chemistry of these worlds. Carbon-based clouds, such as those composed of soot or graphite, can form in carbon-rich atmospheres. These clouds are often found on planets with high carbon-to-oxygen ratios and can affect thermal emission. Ammonia clouds are common on gas giants like Jupiter and Saturn and have been detected on some exoplanets. These clouds form in cooler regions of the atmosphere and can indicate the presence of ammonia gas. Methane clouds are another possibility on cooler exoplanets, especially those with atmospheres rich in methane. These clouds can form in similar conditions to those found on Saturn's moon Titan. Hydrogen sulfide clouds have been detected in the atmospheres of some gas giants. These clouds can contribute to the distinctive color and chemical properties of the planet's atmosphere. Phosphine clouds are of particular interest due to their potential connection to biological processes. While phosphine has been suggested as a biosignature gas, It can also form through abiotic processes in certain atmospheric conditions. Sulfuric acid clouds are well known from Venus and could exist on exoplanets with similar conditions. These clouds can create highly reflective layers and affect the planet's thermal balance. Water ice clouds can form on exoplanets with the right temperature and atmospheric conditions. These clouds are crucial for understanding the potential for water cycles and habitability. Hydrocarbon clouds, composed of complex organic molecules, can form in the atmospheres of planets and moons with significant methane and ethane presence. These clouds play a role in the photochemistry of the atmosphere. Clouds composed of exotic ices, such as carbon dioxide or methane ice, can form on colder exoplanets. These clouds can reflect starlight and contribute to the planet's albedo and climate. Mixed composition clouds, containing a variety of substances, can also exist. The combination of different materials can lead to complex and layered cloud structures with varying optical properties. Studying these exotic clouds provides valuable insights into the atmospheric dynamics and chemistry of exoplanets. Each type of cloud contributes to our understanding of how diverse planetary environments can be and the unique weather systems that can arise. The formation mechanisms of exotic clouds on exoplanets are driven by a variety of factors, including temperature, pressure, and atmospheric composition. These processes begin with the availability of condensable materials in the planet's atmosphere. In hot environments, such as those found on ultra-hot Jupiters, high temperatures can vaporize minerals and metals. As these gases move to cooler regions of the atmosphere, they condense to form clouds. Silicate clouds form when rock-forming minerals vaporize due to extreme heat. As the temperature decreases with altitude, these silicates condense into cloud particles, often at high altitudes. Metal clouds, such as those composed of iron or titanium oxide, form through similar processes. Vaporized metals on the hot day side of a tidally locked planet can condense into clouds as they are transported to the cooler night side. Alkali metal clouds, including sodium and potassium, form in high-temperature atmospheres. These metals vaporize easily and can form clouds that reflect and absorb stellar radiation. Carbon-based clouds, like those composed of soot or graphite, form in carbon-rich atmospheres. High carbon-to-oxygen ratios favor the formation of these clouds, which can impact the planet's thermal emission. Ammonia clouds form in cooler atmospheres, where ammonia gas can condense into droplets. These clouds are common on gas giants and indicate the presence of ammonia in the atmosphere. Methane clouds form under similar conditions to ammonia clouds, typically in cooler environments where methane can condense. These clouds play a significant role in the atmospheric chemistry of the planet. Hydrogen sulfide clouds form when hydrogen sulfide gas, present in some gas giant atmospheres, cools and condenses. These clouds can affect the planet's color and chemical properties. Phosphine clouds, though less common, form in atmospheres where phosphine gas can condense. The formation of these clouds can be influenced by both biological and non-biological processes. Sulfuric acid clouds form in highly acidic environments, like those on Venus. These clouds result from the condensation of sulfur dioxide and water vapor, creating reflective and highly acidic cloud layers. Water ice clouds form in atmospheres with sufficient water vapor and low enough temperatures. These clouds are crucial for understanding water cycles and potential habitability on exoplanets. Hydrocarbon clouds form in atmospheres rich in methane and ethane, where these gases can condense into complex organic molecules. These clouds play a key role in the photochemistry of the atmosphere. Exotic ice clouds, such as those composed of carbon dioxide or methane ice, form on colder exoplanets. These ices can condense at low temperatures, creating reflective cloud layers. Mixed composition clouds form when multiple substances condense at different altitudes or temperatures. These clouds can have complex and layered structures with varying optical properties. Understanding the formation mechanisms of exotic clouds on exoplanets helps scientists model their atmospheres and predict weather patterns. These insights contribute to our broader knowledge of planetary climates and the diversity of environments in the universe. Exotic clouds play a crucial role in shaping the climate of exoplanets. They affect the planet's energy balance by reflecting and absorbing stellar radiation. Silicate clouds, found on ultra-hot Jupiters, reflect a significant amount of light, reducing the heat reaching the lower atmosphere and surface. This reflection can create cooler temperatures below the cloud layer. Metal clouds, like those composed of iron and titanium oxide, can absorb and re-radiate heat. This process can lead to temperature inversions, where the temperature increases with altitude, affecting atmospheric circulation. Alkali metal clouds, such as those made of sodium and potassium, impact the planet's albedo. Their reflective properties influence how much sunlight the planet absorbs or reflects back into space. Carbon-based clouds, including soot and graphite, absorb heat and contribute to warming the atmosphere. This warming effect can alter the planet's thermal structure and weather patterns. Ammonia clouds, common on gas giants, reflect sunlight and create a cooling effect. This cooling can influence the atmospheric dynamics and heat distribution on the planet. Methane clouds also reflect sunlight and contribute to cooling. Their presence can significantly impact the thermal balance and climate, especially on cooler exoplanets. Hydrogen sulfide clouds, with their distinct color and chemical properties, can affect the overall appearance and atmospheric chemistry of the planet. These clouds play a role in the planet's climate by influencing temperature and weather patterns. Phosphine clouds, though rarer, can indicate complex chemical interactions. The formation of these clouds can affect the planet's albedo and contribute to warming or cooling, depending on their composition and altitude. Sulfuric acid clouds, like those on Venus, are highly reflective and create a strong greenhouse effect. This effect traps heat in the lower atmosphere, leading to extremely high surface temperatures. Water ice clouds are critical for moderating climates on planets with potential for liquid water. These clouds reflect sunlight and can help stabilize temperatures, contributing to more habitable conditions. Hydrocarbon clouds, found in methane-rich atmospheres, absorb and scatter sunlight, impacting the thermal structure. These clouds can drive unique weather systems and influence the planet's climate. Exotic ice clouds, such as those composed of carbon dioxide or methane ice, create reflective layers that cool the atmosphere. Their formation can lead to seasonal changes in climate as they form and dissipate. Mixed composition clouds add complexity to the planet's climate system. The interaction of different cloud types can create diverse weather patterns and influence the overall climate stability. The presence and distribution of these exotic clouds help scientists understand the climate dynamics of exoplanets. By studying these clouds, researchers can infer the atmospheric composition, thermal structure, and potential habitability of distant worlds. Understanding the role of exotic clouds in planetary climates enhances our ability to model and predict weather patterns on exoplanets. This knowledge is crucial for assessing the conditions that may support life, and for understanding the diverse environments that exist beyond our solar system. Exotic clouds on exoplanets significantly impact visibility and the observations we make from Earth. These clouds can obscure or alter the spectral signatures we rely on to study these distant worlds. Silicate clouds, with their high reflectivity, can make it difficult to observe the deeper layers of an exoplanet's atmosphere. They reflect a lot of the incoming starlight, creating a bright, reflective layer that obscures underlying features. Metal clouds, such as those composed of iron or titanium oxide, absorb and re-emit radiation, complicating the interpretation of thermal emission spectra. This absorption can mask the signatures of other atmospheric components. Alkali metal clouds, like sodium and potassium, create strong absorption lines in the visible spectrum. These lines can dominate the spectral data, making it challenging to detect other elements and compounds. Carbon-based clouds, including soot and graphite, absorb a significant amount of light, darkening the planet's appearance. This absorption can reduce the overall brightness, affecting the quality of observational data. Ammonia clouds, prevalent on gas giants, scatter light and create diffuse reflection patterns. This scattering can blur the spectral features and complicate the analysis of the planet's atmosphere. Methane clouds also scatter and absorb light, affecting the visibility of the planet's surface and lower atmosphere. These clouds can introduce noise into the spectral data, making it harder to identify specific compounds. Hydrogen sulfide clouds, with their unique spectral signatures, can interfere with the detection of other gases. The presence of these clouds can skew the observed spectral lines, leading to potential misinterpretations. Phosphine clouds, though rare, can create distinct absorption features that dominate the spectrum. These features can obscure the detection of other important molecules and complicate the analysis. Sulfuric acid clouds, highly reflective and dense, can make it difficult to penetrate the cloud layers with optical and infrared observations. This reflectivity can limit our ability to gather data on the lower atmospheric layers. Water ice clouds can enhance the reflectivity of a planet, increasing its albedo and affecting its observed brightness. These clouds can mask the spectral features of gases below the cloud layer. Hydrocarbon clouds, by absorbing and scattering light, impact the visibility of the planet's surface and atmospheric composition. The presence of these clouds can alter the apparent color and brightness of the planet.
Exotic ice clouds, such as those of carbon dioxide or methane ice, create reflective layers that obscure lower atmospheric details. These clouds complicate the interpretation of seasonal climate changes.
Mixed composition clouds add a layer of complexity to observational data. The interaction of different cloud types can create variable reflectivity and absorption patterns, making it harder to draw clear conclusions. The presence of these clouds necessitates advanced techniques for observation and data analysis. Scientists use multi-wavelength observations to penetrate different cloud layers and gather comprehensive atmospheric data. Understanding the impact of exotic clouds on visibility and observations is crucial for accurately characterizing exoplanet atmospheres. These insights help refine our models and improve the precision of our data, enhancing our knowledge of the diverse and complex environments on distant worlds. Kepler 7b is an exoplanet located about 1,000 light-years from Earth in the constellation Lyra. It is known for its large size and unusually low density, making it one of the puffy planets. One of the most intriguing features of Kepler 7b is its reflective cloud cover. Observations have shown that its atmosphere has a high albedo, indicating the presence of clouds that reflect a lot of light. The Kepler Space Telescope first detected Kepler 7b using the transit method, observing the dips in starlight as the planet passed in front of its host star. These transits help determine the planet's size and orbit. Further observations using the Spitzer Space Telescope provided insights into the planet's atmospheric composition. These observations indicated that the reflective clouds are likely composed of silicate particles. The cloud cover on Kepler 7b is not uniform. Data suggest that the western hemisphere of the planet is more reflective than the eastern hemisphere, indicating asymmetrical cloud distribution. This asymmetry in cloud cover leads to temperature variations across the planet. The reflective clouds cool the western hemisphere, while the eastern hemisphere with fewer clouds remains warmer. The presence of silicate clouds suggests high temperatures in the upper atmosphere, where these particles can condense. These clouds likely form at high altitudes, reflecting sunlight and creating the observed high albedo. Kepler 7b's low density indicates that it has a thick, extended atmosphere. This puffy atmosphere is likely filled with hydrogen and helium, with cloud layers of heavier elements like silicates. The reflective clouds have a significant impact on the planet's climate and thermal dynamics. They reduce the amount of stellar radiation reaching the lower atmosphere, affecting heat distribution and atmospheric circulation. The study of Kepler 7b provides valuable insights into the formation and behavior of clouds on hot Jupiters. It helps scientists understand how high-altitude clouds influence the overall climate of these planets. Kepler 7b's unique cloud cover also affects its observational characteristics. The high albedo makes the planet appear brighter in optical wavelengths, aiding in its detection and study. The variability in cloud cover across the planet offers a natural laboratory for studying atmospheric dynamics and weather patterns on exoplanets. It shows how cloud formation and distribution can vary on a global scale. Future observations with more advanced telescopes aim to study Kepler 7b in greater detail. These observations will focus on the composition, altitude, and dynamics of its cloud cover, providing deeper insights into its atmosphere. Kepler 7b serves as a case study for understanding the diverse atmospheric conditions that can exist on exoplanets. Its reflective clouds and low density challenge traditional models of planetary formation and composition. The ongoing research on Kepler 7b enhances our knowledge of exoplanetary atmospheres and their impact on planetary climates. Each new discovery contributes to the broader understanding of the complex and varied environments beyond our solar system. High-gravity planets are worlds with surface gravity significantly stronger than Earth's. This increased gravity is usually due to the planet's larger mass and sometimes its smaller radius, leading to a higher density. These planets can be either gas giants or rocky super-Earths. Gas giants like Jupiter and Saturn have strong gravitational pulls due to their immense masses, despite their gaseous compositions. Super-Earths are rocky exoplanets with masses greater than Earth's, but smaller than those of Uranus and Neptune. Their higher density and mass result in stronger gravitational forces on their surfaces. The surface gravity of a planet affects many aspects of its environment and potential habitability. High gravity influences atmospheric retention, surface pressure, and even geological activity. On high-gravity planets, the atmosphere is held more tightly to the planet's surface. This can lead to denser atmospheres with higher pressures, affecting weather patterns and climate. The strong gravitational pull can impact the planet's geological features. Mountains and landforms may be lower and broader compared to those on Earth, as the high gravity pulls them down. High gravity also affects the escape velocity, making it more difficult for atmospheric particles to escape into space. This can result in thicker atmospheres and different atmospheric compositions compared to low-gravity planets. Biological processes on high-gravity planets would be different from those on Earth. The increased gravity would affect the structure and function of potential life forms, likely leading to stronger, more robust organisms. Water and other liquids would behave differently under high-gravity conditions. Oceans and lakes might be shallower, and the behavior of waves and currents would be influenced by the stronger gravitational forces. The weather on high-gravity planets could be more extreme due to the dense atmospheres and higher surface pressures. Wind speeds and storm intensities might differ significantly from those on Earth. The high pressure at the surface of these planets can affect chemical reactions and the formation of minerals. This can lead to unique geological and chemical processes not found on lower gravity worlds. Exploration of high-gravity planets poses significant challenges for spacecraft and probes. The stronger gravitational pull requires more energy for landing and takeoff, complicating mission designs. High-gravity planets offer unique opportunities to study planetary formation and evolution. Their characteristics provide insights into the diversity of planetary systems and the range of possible environments. Understanding high-gravity planets helps scientists refine models of planet formation and atmospheric dynamics. It broadens our knowledge of how planets develop under different gravitational conditions. Research on high-gravity planets contributes to the search for habitable worlds. By studying these planets, scientists can better understand the factors that influence habitability and the potential for life in diverse environments. Atmospheric pressure and density on high-gravity planets are significantly influenced by their strong gravitational pull. These factors play a crucial role in shaping the planet's weather, climate, and potential habitability. The higher gravity of these planets compresses the atmosphere more than on Earth, resulting in much higher surface pressure. This increased pressure can lead to denser atmospheres with greater concentrations of gases. A dense atmosphere can affect the transmission of heat, leading to different temperature gradients and thermal structures compared to lower gravity planets. This can impact weather patterns and climate stability. High atmospheric pressure can influence the behavior of gases and liquids on the planet's surface. It can cause gases to dissolve more readily in liquids, affecting chemical reactions and potentially the formation of oceans or lakes. The density of the atmosphere also affects how light and heat are absorbed and scattered. A denser atmosphere can trap more heat, potentially leading to a stronger greenhouse effect and higher surface temperatures. Wind patterns on high-gravity planets may be altered by the increased density and pressure of the atmosphere. The thicker air can result in more intense and sustained wind systems, possibly leading to frequent and severe storms. Cloud formation is influenced by atmospheric pressure and density. High-gravity planets may have thicker cloud layers due to the higher availability of condensing gases, impacting weather and climate. The high pressure can also affect the planet's magnetic field and its interactions with the stellar wind. A stronger atmosphere may provide better protection against stellar radiation, influencing the planet's potential habitability. Life forms, if they exist, would need to adapt to the high atmospheric pressure. Organisms might develop stronger structures to withstand the pressure, and their respiratory systems would need to be efficient at extracting oxygen from the dense air. High pressure can influence the types of minerals and rocks that form on the planet's surface. Certain minerals that require high pressure to form might be more common, providing clues about the planet's geological history. The atmospheric composition on high-gravity planets might include heavier gases that are less common on Earth. The high pressure can keep these gases in the atmosphere, contributing to a unique chemical environment. Exploring high-gravity planets poses challenges for spacecraft due to the dense atmosphere. Entry, descent, and landing require careful planning to account for the increased atmospheric drag and pressure. The study of atmospheric pressure and density on these planets helps scientists understand the range of possible climates and environments. It also provides insights into the physical processes that govern planetary atmospheres. Observations of high-gravity planets can reveal variations in atmospheric pressure and density, offering clues about the planet's composition, structure, and evolution. Understanding how atmospheric pressure and density affect high-gravity planets is essential for building accurate models of these worlds. This knowledge enhances our ability to predict their behavior and potential for supporting life. Future missions to high-gravity planets will continue to investigate these factors, providing deeper insights into the complex interplay between gravity, atmosphere, and planetary environment. Now, weather patterns in high-gravity environments are shaped by the planet's strong gravitational pull and dense atmosphere. These conditions create unique and often extreme weather phenomena. The high gravity leads to a thicker atmosphere, which can enhance the greenhouse effect. This can result in higher surface temperatures and more intense weather systems compared to lower gravity planets. Wind speeds may be higher on high-gravity planets due to the increased density of the atmosphere. The thick air can sustain strong winds, potentially leading to frequent and powerful storms. Cloud formation is influenced by the dense atmosphere. High-gravity planets may have extensive cloud cover, with clouds forming at multiple atmospheric layers, contributing to complex weather patterns. Precipitation on these planets can be more intense due to the higher pressure. Rainfall could be heavier and more frequent, affecting surface erosion and the planet's hydrological cycle. The strong gravitational pull can lead to faster atmospheric circulation. This means that weather systems can develop and dissipate more quickly, resulting in rapidly changing weather conditions. High gravity can also impact the planet's jet streams. These fast-moving air currents, driven by temperature differences, can be stronger and more stable, influencing global weather patterns. Temperature gradients between the equator and the poles can be more pronounced in high-gravity environments. This can drive stronger seasonal weather changes and more extreme temperature variations. The high pressure can affect the composition and behavior of storms. Thunderstorms, for example, might be more intense, with higher energy outputs and stronger lightning activity. Weather patterns on high-gravity planets could also include more severe cyclones and hurricanes. The dense atmosphere can sustain these systems for longer periods, leading to prolonged and destructive weather events. High gravity affects the vertical structure of the atmosphere. Convection currents, which drive the movement of heat and moisture, can be more vigorous, leading to dynamic and turbulent weather systems. The presence of a thick atmosphere can also influence surface winds. These winds can be stronger and more persistent, shaping the landscape through erosion and deposition of materials. Weather patterns might be more stable in some high-gravity environments due to the efficient heat distribution. However, this stability can also mean that when extreme weather does occur, it is more intense and impactful. The increased atmospheric pressure can lead to unique weather phenomena, such as metallic or hydrocarbon rain, depending on the planet's atmospheric composition. These types of precipitation would significantly affect the planet's surface. Understanding weather patterns in high-gravity environments helps scientists predict the climate and potential habitability of these planets. It provides insights into how different physical conditions shape the behavior of planetary atmospheres. Ongoing research and observations aim to uncover more about these unique weather patterns. Future missions and advanced telescopes will continue to provide valuable data, enhancing our understanding of the diverse climates in our universe. The potential for life on high-gravity planets is a fascinating area of study. These planets offer unique environments that could support life, despite their extreme conditions. High gravity affects the structure and physiology of potential life forms. Organisms would need to be robust, with strong skeletal and muscular systems to withstand the intense gravitational forces. The dense atmosphere of high-gravity planets could protect life forms from harmful stellar radiation. This thick atmosphere could act as a shield, similar to how Earth's atmosphere protects us. Water, essential for life as we know it, might behave differently under high gravity. Bodies of water could be shallower and more stable, providing a consistent environment for aquatic life. The strong gravity would influence the behavior of gases and liquids, potentially leading to unique biochemical processes. Life forms might evolve to utilize these processes in ways that are fundamentally different from life on Earth. High atmospheric pressure could affect respiration and metabolism. Organisms might have more efficient respiratory systems to extract oxygen from the dense air, and their metabolic processes could be adapted to the high pressure. The stable, dense atmosphere could lead to a more uniform climate, reducing extreme weather fluctuations. This stability might create more predictable and hospitable conditions for life to develop and thrive. Energy sources such as geothermal activity could be more pronounced on high-gravity planets. This geothermal heat could provide a steady source of energy for life, especially if the planet is far from its star.
The presence of high gravity could influence the development of complex ecosystems. Life forms might evolve to take advantage of environments and abundant resources.
The unique chemical environment created by high gravity could lead to the development of novel biochemical compounds. These compounds might support life in ways that are not possible on lower gravity planets. The potential for subsurface oceans on high-gravity planets is another intriguing possibility. These oceans, protected by a thick ice layer, could harbor life in a stable, isolated environment. High gravity could affect the planet's magnetic field and its interactions with the stellar wind. A strong magnetic field might provide additional protection from cosmic radiation, further enhancing the planet's habitability. Life on high-gravity planets might also exhibit unique reproductive and developmental processes. The strong gravity could influence the growth and development of organisms in ways that differ significantly from Earth. The discovery of life on high-gravity planets would expand our understanding of the adaptability and resilience of life. It would show that life can thrive under a wide range of physical conditions. Exploring high-gravity planets for signs of life involves studying their atmospheres, surfaces, and potential subsurface environments. Advanced telescopes and future missions will play a crucial role in this exploration. Understanding the potential for life on high-gravity planets helps scientists refine the criteria for habitability. It broadens the scope of the search for extraterrestrial life, highlighting the diverse environments where life might exist. Rogue planets, also known as free-floating planets, are celestial bodies that do not orbit a star. Instead, they drift through space, unattached to any solar system. These planets are thought to be ejected from their original star systems due to gravitational interactions or collisions. As a result, they wander the galaxy independently. Without a star to provide light and heat, rogue planets exist in perpetual darkness and extreme cold. Their environments are vastly different from those of planets within solar systems. Despite the absence of stellar warmth, rogue planets may retain internal heat from their formation. This heat can come from radioactive decay or residual heat from when the planet formed. And some rogue planets might have thick atmospheres that insulate their surfaces, trapping heat and potentially allowing for subsurface oceans. These oceans could exist under layers of ice, similar to those on some moons in our solar system. The lack of a star means that rogue planets do not experience day-night cycles. Their environments are stable in terms of illumination, but can be dynamically active due to internal geological processes. Detection of rogue planets is challenging because they do not emit or reflect much light. Scientists use methods like gravitational microlensing, where the planet's gravity bends and magnifies the light of distant stars, to identify them. Rogue planets can vary widely in size and composition. They might be gas giants, similar to Jupiter, or rocky planets, similar to Earth, with various atmospheres and surface conditions. The discovery of rogue planets provides insights into planetary formation and the dynamics of star systems. Their existence suggests that planet formation is a common and sometimes turbulent process. Rogue planets may also offer clues about the distribution of planets in the galaxy. Understanding their prevalence helps scientists estimate the total number of planets, both bound and free-floating. These planets might host unique forms of life if they have the right conditions. Subsurface oceans, heated by internal sources, could provide stable environments where life might evolve. Studying rogue planets enhances our understanding of planetary diversity and the range of environments where planets can exist. It broadens the scope of planetary science beyond traditional solar systems. The isolation of rogue planets makes them fascinating objects of study. They represent a different kind of planetary evolution, one that occurs without the influence of a central star. Future missions and advanced telescopes aim to detect and study more rogue planets. These observations will provide valuable data about their characteristics and the processes that lead to their formation. Understanding rogue planets contributes to the broader quest to understand the universe. These free-floating worlds challenge our notions of planetary systems and highlight the incredible diversity of planets in the galaxy. Sources of internal heat on rogue planets are crucial for maintaining their geologic and potentially biologic activity. Without the external heat from a star, these planets rely entirely on their internal energy. One primary source of internal heat is radioactive decay. Elements like uranium, thorium, and potassium decay over time, releasing heat that warms the planet's interior. Gravitational contraction, also known as the Kelvin-Helmholtz mechanism, can generate heat in the planet's core. As the planet slowly contracts under its own gravity, the potential energy is converted into thermal energy. Residual heat from planetary formation can also contribute. When planets form, they accumulate significant heat from the accretion of material and collisions with other bodies. This heat can take billions of years to dissipate. Tidal heating is another potential source of internal heat, though it typically requires gravitational interaction with another object. In a rogue planet's past, such interactions could have provided significant heat. Chemical differentiation, where heavier elements sink towards the core and lighter elements rise, can release heat through friction and chemical reactions. This process contributes to the thermal evolution of the planet. Hydrothermal vents on the ocean floor can be heated by the planet's internal heat sources. These vents might provide energy and nutrients, creating potential habitats for life in subsurface oceans. Mantle convection, driven by internal heat, can create geological activity such as volcanism. Volcanic activity can release heat and gases, potentially maintaining a subsurface ocean under an icy crust. The heat from radioactive decay can be significant in smaller rocky planets, while larger gas giants might rely more on gravitational contraction and residual heat. The balance of these sources varies with planet composition and size. Understanding the balance of these heat sources helps scientists model the thermal evolution of rogue planets. These models are crucial for predicting the geologic and potential biologic activity of these worlds. Heat flow from the interior to the surface affects the planet's surface conditions. In the absence of stellar heat, this internal heat flow determines the potential for liquid water and habitable environments. The presence of internal heat can sustain a liquid water ocean beneath an ice layer. This environment could be similar to the subsurface oceans of moons like Europa and Enceladus in our solar system. Heat from the core can create a dynamo effect, generating a magnetic field. This magnetic field can protect the planet from cosmic radiation, which is particularly important for rogue planets lacking a stellar magnetosphere. The study of internal heat sources on rogue planets can also provide insights into the formation and evolution of other planetary bodies, both within and outside solar systems. Future missions and advanced observational techniques aim to detect signs of internal heat on rogue planets. These efforts will enhance our understanding of these isolated worlds and their potential to harbor life. Understanding the internal heat of rogue planets is crucial for comprehending their geology, potential habitability, and the diverse processes that sustain them in the cold depths of interstellar space. Weather on rogue planets without a host star is driven entirely by internal heat sources. These planets lack the external heat from a star, leading to unique atmospheric and surface conditions. Without a star, rogue planets experience perpetual darkness. This lack of sunlight means that weather patterns are not influenced by day-night cycles, creating a stable but cold environment. The primary source of energy for weather on rogue planets is internal heat, which can drive convection currents in the atmosphere, These currents can create winds and storms, albeit different from those on star-bound planets. The surface temperature on rogue planets can vary depending on the efficiency of heat transfer from the interior. Areas with active geothermal features may be warmer, influencing localized weather patterns. Thick atmospheres on rogue planets can trap internal heat, maintaining relatively stable surface temperatures. This greenhouse effect, while different from solar-driven planets, can still create a warm enough environment to support liquid water. Hydrothermal activity on the surface or beneath ice layers can release gases, contributing to atmospheric dynamics. These releases can drive wind patterns and create weather systems centered around geothermal hotspots. Storms on rogue planets could be fueled by heat from volcanic activity. The release of heat and gases from volcanoes can create turbulent weather, with ash clouds and localized storms. The lack of solar radiation means that cloud formation is driven by internal heat and the presence of atmospheric moisture. Clouds might form over geothermal vents, creating localized weather patterns. Wind patterns on rogue planets are influenced by the planet's rotation and the distribution of heat sources. These winds can transport heat and gases around the planet, leading to complex atmospheric circulation. The absence of solar-driven evaporation and precipitation cycles changes the nature of rain and snow. Precipitation might be driven by geothermal heat, with localized rain or snow around warmer regions. Seasons on rogue planets are likely non-existent or minimal, as they are not influenced by a star. Weather patterns could remain relatively stable over long periods, with slow changes driven by geological processes. The atmospheric composition of rogue planets can be unique, influenced by the planet's internal chemistry. Gases released from the interior, such as methane or sulfur compounds, can dominate the atmosphere and affect weather patterns. The study of weather on rogue planets helps scientists understand how atmospheres behave without solar influence. These insights can be applied to other planets and moons with limited sunlight. Future observations and models aim to simulate the weather on rogue planets. These studies will provide a better understanding of how internal heat drives atmospheric dynamics in the absence of a star. Understanding weather on rogue planets expands our knowledge of planetary atmospheres and the potential for diverse environments in the universe. It highlights the adaptability of planetary systems to a wide range of conditions. The potential for subsurface oceans on rogue planets is a fascinating possibility. Despite the absence of a host star, these planets might harbor liquid water beneath their icy crusts. Internal heat from radioactive decay and residual formation heat could keep these subsurface oceans warm. This heat prevents the water from freezing solid, maintaining a liquid state beneath the ice. Thick ice layers insulate the subsurface ocean, trapping heat and creating a stable environment. The ice acts as a barrier, protecting the liquid water from the extreme cold of space. Geothermal activity can provide additional heat to sustain these subsurface oceans. Hydrothermal vents on the ocean floor could release heat and nutrients, supporting potential ecosystems. The presence of subsurface oceans on rogue planets could offer habitats for life. These environments are isolated from the harsh conditions of space, potentially allowing life to thrive. Life forms in subsurface oceans would need to adapt to complete darkness. Chemosynthesis, using chemicals from hydrothermal vents, could replace photosynthesis as the primary energy source. Studying similar environments on Earth, such as deep-sea hydrothermal vents, provides insights into how life might exist in these dark, high-pressure environments. Subsurface oceans might also contain unique chemical compositions, influenced by the planet's geology. These compositions could support diverse biological processes and life forms. The search for subsurface oceans on rogue planets involves detecting signs of internal heat and potential liquid water. Instruments that measure gravitational fields, magnetic fields, and thermal emissions are crucial for this research. The icy crust of rogue planets might show signs of movement or cracking, indicating the presence of a liquid ocean beneath. These features are similar to those observed on icy moons like Europa and Enceladus. Future missions could aim to explore these icy surfaces, using landers or probes to drill through the ice and sample the underlying water. These missions would provide direct evidence of subsurface oceans. The discovery of subsurface oceans on rogue planets would expand our understanding of habitable environments, It would show that life can exist in a variety of conditions, not just those similar to Earth. The potential for subsurface oceans also raises questions about the formation and evolution of rogue planets. Understanding how these oceans form and are sustained can provide insights into the dynamics of planetary systems. Research into subsurface oceans on rogue planets complements the study of similar environments in our solar system. This comparative planetology approach enhances our knowledge of where and how life might exist beyond Earth. The possibility of subsurface oceans on rogue planets highlights the diversity of planetary environments. It underscores the importance of exploring all potential habitats in the search for extraterrestrial life. In this video, we delved into the fascinating and extreme weather phenomena found on exoplanets, far beyond our solar system. We began by defining exoplanets and explaining the importance of studying their weather patterns. From there, we explored various known exoplanet weather phenomena, comparing these with Earth's weather to highlight the vast differences and unique conditions that exist in other planetary systems. We covered the transit method and radial velocity method, two primary techniques used to detect exoplanets and infer their atmospheric properties. We also discussed direct imaging and atmospheric spectroscopy, which allow scientists to observe exoplanets more directly and analyze their atmospheric compositions in greater detail. These methods are essential for understanding the diverse climates and potential habitability of these distant worlds. Moving on, we examined the characteristics of hot Jupiters, focusing on temperature extremes and how these conditions influence their atmospheric dynamics. We then looked into the role of tidal locking, where a planet's rotation period matches its orbit around its star, leading to permanent day and night sides. This unique situation creates extreme climate variations and complex weather patterns. We also explored the formation of exotic clouds on exoplanets, including metal clouds and other unusual compositions. These clouds have significant impacts on planetary climates and observational visibility, affecting how we study and understand these distant environments. Specific case studies, such as WASP 121b and Kepler 7b, provided real examples of these phenomena in action. The video further discussed high-gravity planets, detailing how increased surface gravity influences atmospheric pressure, weather patterns, and the potential for life. We also covered rogue planets, those that drift through space without a host star, and examined the sources of their internal heat and the possibility of subsurface oceans. Finally, we considered the potential for life on these diverse worlds, emphasizing the adaptability of life in extreme conditions and the importance of continuing our exploration. The potential for subsurface oceans on rogue planets presents exciting possibilities for finding life in the most unexpected places. Thank you for joining us on this journey through the extreme weather of exoplanets. If you enjoyed this video, please like and subscribe to our channel for more content on space exploration and planetary science. Don't forget to check out the rest of our videos for more fascinating insights into the wonders of the universe.